Imagine standing on a beach at midnight, looking up at the star-filled sky. You're holding a handful of sand, feeling the countless tiny grains slip through your fingers. Now here's something that will shatter your perception of reality. There are more stars in the universe than grains of sand in your hand, on that beach, and on every beach that has ever existed on Earth. But that's just the beginning of our cosmic journey. We're going to explore 30 facts about the universe that are so mind-bending, so utterly incredible, that they'll forever change how you see reality. These aren't just numbers and statistics. They're revelations about the nature of existence itself. From the bizarre physics that govern time and space, to the mysterious dark forces that control the cosmos, to the mind-boggling scales that make our entire planet seem like less than a speck of dust. You think you know big? You think you understand time? You think you comprehend what it means to exist? Prepare to have everything you thought you knew turned upside down. We're about to journey through black holes where time stops, explore realms where diamonds rain from the sky, and discover that you are literally made from the hearts of dying stars. Fact 1. The universe contains 2 trillion galaxies. Welcome to an extraordinary journey through the cosmos, where we'll explore mind-bending facts that will forever change how you see the universe. Let's begin with perhaps the most staggering revelation of modern astronomy. Our observable universe contains approximately 2 trillion galaxies. To put this number into perspective, imagine trying to count to 2 trillion. If you counted one number every second without stopping, it would take you over 63,000 years to reach 2 trillion. Each of these galaxies is a massive collection of stars, planets, gas, dust, and dark matter, bound together by gravity. Our own Milky Way galaxy, which contains an estimated 100 to 400 billion stars, is just one ordinary galaxy among these 2 trillion cosmic islands. The scale becomes even more incomprehensible when we consider that galaxies aren't evenly distributed throughout space. They cluster together in groups and superclusters, connected by vast filaments of dark matter that form the cosmic web. This number comes from the Hubble Space Telescope's deep field observations, where astronomers pointed the telescope at seemingly empty patches of sky for extended periods. What they discovered was astounding. Even the darkest regions of space were teeming with distant galaxies. Each pinpoint of light in these deep field images represents an entire galaxy containing billions of stars, each potentially hosting planetary systems. The process of discovering these galaxies required incredible patience and precision. Scientists would aim Hubble at a patch of sky that appeared completely empty to ground-based telescopes, then let it stare at that single spot for days or even weeks, collecting every photon of light that arrived. Slowly, ghostly images of distant galaxies would emerge from the darkness, like developing photographs in a cosmic dark room. Some of these galaxies are so far away that their light has been traveling for over 13 billion years to reach us, showing us what the universe looked like when it was just a cosmic infant. The implications of 2 trillion galaxies are profound for our understanding of cosmic evolution and the potential for life. If even a tiny fraction of the stars in these galaxies have planets, and even a minuscule percentage of those planets harbor life, the universe could be teeming with biological activity. The sheer scale suggests that life, in some form, might be common throughout the cosmos, even if intelligent life remains rare. What's even more remarkable is that this 2 trillion number only represents the observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang. The actual universe may be infinite, containing an infinite number of galaxies beyond our cosmic horizon. As our observational capabilities improve, and we peer deeper into space, we continue to discover that the universe is far larger and more complex than we ever imagined. The distribution of these 2 trillion galaxies also tells us about the universe's history and future. In the early universe, galaxies were smaller and more numerous. Over billions of years, many have merged through gravitational interactions, creating the larger galaxies we see today. This process continues, and our own Milky Way is destined to collide with the Andromeda Galaxy in approximately 4.5 billion years, eventually merging into a single, larger galaxy. Consider the diversity among these 2 trillion galaxies. Some are massive elliptical galaxies containing trillions of stars, their central regions packed so densely with ancient red giants that they glow like cosmic cities. Others are spiral galaxies like our own, with graceful arms swept back by rotation, nurseries where new stars are constantly being born. Still others are irregular galaxies, chaotic collections of stars torn apart by gravitational encounters with their neighbors. Each galaxy represents a unique experiment in cosmic evolution, shaped by its particular history of star formation, black hole growth, and gravitational interactions. Some galaxies are actively forming stars at incredible rates, converting gas and dust into new suns at a pace thousands of times faster than our Milky Way. Others are effectively dead, their star formation having ceased billions of years ago, leaving them filled with aging stellar populations that slowly fade over cosmic time. The supermassive black holes at the centers of these galaxies add another layer of complexity. These cosmic monsters, millions or billions of times more massive than our Sun, regulate star formation throughout their host galaxies through powerful jets and winds that can heat or expel the raw materials needed to make new stars. The relationship between galaxies and their central black holes is one of the most active areas of research in modern astrophysics. When we contemplate 2 trillion galaxies, we're not just talking about 2 trillion collections of stars. We're talking about 2 trillion laboratories where the fundamental processes of the universe play out. The birth and death of stars, the formation of heavy elements, the growth of black holes, and potentially the emergence of life. Each galaxy is a complete world unto itself, with its own history, its own cast of stellar characters, and its own destiny written in the laws of physics. Fact 2. More stars exist than grains of sand on all Earth's beaches. One of the most poetic comparisons in astronomy involves counting stars versus grains of sand. When Carl Sagan made this comparison famous, he was highlighting the incomprehensible scale of the universe in terms that humans could at least attempt to visualize. The numbers are truly staggering. Astronomers estimate there are approximately 10 to the 24th power stars in the observable universe, while the total number of grains of sand on all Earth's beaches is estimated at about 7.5 times 10 to the 18th power. To understand these numbers, let's break them down systematically. A typical grain of sand is about 0.1 to 2 millimeters in diameter. Earth has approximately 750,000 kilometers of coastline, though this varies depending on how precisely you measure. When scientists calculate the volume of sand, on all beaches, dunes, and coastal areas, they consider depth, width, and the varying grain sizes. The calculation involves complex estimations, but the consensus places the number of sand grains at roughly 7.5 quintillion. The process of counting sand grains isn't as straightforward as it might seem. Scientists have to account for different types of beaches, from the fine white sands of tropical paradises to the coarse black volcanic beaches of Hawaii. They must consider how deep the sand goes, which varies dramatically from place to place. Some beaches have sand that extends hundreds of meters inland and dozens of meters deep, while others are thin veneers over rocky substrates. Now consider the stars. In our Milky Way galaxy alone, there are an estimated 100 to 400 billion stars. This number itself is derived from careful observations of stellar density in different regions of our galaxy, combined with models of galactic structure. Multiply this by the 2 trillion galaxies in the observable universe, and you get numbers that dwarf the sand grain count by roughly 100,000 times. This means for every single grain of sand on every beach on Earth, there are 100,000 stars in the observable universe. The variety among these stars is extraordinary and humbling. Our Sun is considered an average middle-aged star, but the universe contains red dwarfs that will burn for trillions of years, massive blue giants that live fast and die young in spectacular supernova explosions, and ancient red giants nearing the end of their stellar lives. Some stars are barely larger than Jupiter, while others are so massive they could engulf our entire solar system within their outer atmospheres. Each star represents a potential solar system. Recent discoveries by the Kepler Space Telescope and other planet-hunting missions suggest that most stars host at least one planet. If this holds true across the universe, the number of planets would exceed the number of stars, making the cosmic inventory even more mind-boggling. Consider that among these countless worlds, there could be planets with oceans deeper than Earth's, atmospheres stranger than we can imagine, and perhaps life forms that would challenge our understanding of biology itself. The life cycle of these countless stars creates the very elements that make life possible. In the cores of massive stars, nuclear fusion forges elements heavier than hydrogen and helium. When these stars explode as supernovas, they scatter these elements throughout space, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in the nuclear furnaces of long-dead stars. But the comparison to sand grains reveals something even more profound about our place in the cosmos. Every grain of sand was once part of a larger rock, weathered by wind and water over millions of years, carried by rivers to the sea, and shaped by countless tides. Each grain has its own history, its own journey from mountain to beach. Similarly, every star has its own story. Born in a nebula, living its life according to the laws of nuclear physics, and eventually dying in ways that depend on its mass and composition. The timescales involved in both sand formation and stellar evolution dwarf human experience. A grain of sand might take millions of years to travel from its origin in an eroded mountain to its final resting place on a beach. A star like our Sun burns for about 10 billion years, while the most massive stars live only a few million years, and the smallest red dwarfs can survive for over 1 trillion years. These timescales remind us that we exist in just a fleeting moment of cosmic history. When you hold a handful of sand, you're holding millions of tiny pieces of Earth's geological history. When you look up at the night sky, you're seeing the light from nuclear furnaces scattered across billions of years of cosmic time. The fact that there are more stars than sand grains isn't just an interesting statistic. It's a reminder that we live in a universe of unimaginable richness and complexity, where every point of light in the sky represents an entire world of physics, chemistry, and potentially biology. This comparison also highlights how our perspective shapes our understanding. To an ant, a single grain of sand might seem enormous. To us, the same grain is nearly invisible. To a being capable of perceiving the entire universe at once, our Sun might be just another unremarkable point among the vast stellar multitude. The sand-star comparison reminds us to remain humble in the face of cosmic immensity, while simultaneously marveling at our ability to comprehend and measure such vastness. Fact 3. Your head ages faster than your feet due to gravity. Einstein's theory of general relativity revealed one of the most counterintuitive aspects of reality. Time is not constant, but varies depending on gravitational fields. This means that different parts of your body are literally aging at slightly different rates. Your head, being farther from Earth's center of mass, experiences slightly weaker gravity than your feet, causing time to pass infinitesimally faster for your head. The difference amounts to approximately 90 billionths of a second per year. While this might seem like an academic curiosity with no practical relevance, the reality is that this effect is measurable with atomic clocks and must be accounted for in numerous modern technologies. The Global Positioning System, or GPS, which has become indispensable for navigation, commerce, and emergency services, would fail catastrophically without corrections for gravitational time dilation. GPS satellites orbit at an altitude of approximately 20,000 kilometers, where Earth's gravitational field is significantly weaker than at the surface. The mathematics behind this phenomenon emerge from Einstein's revolutionary insight that space and time are interwoven into a four-dimensional fabric called space-time. Massive objects like Earth warp this fabric, creating what we experience as gravity. The deeper you are in a gravitational well, closer to a massive object, the more severely space-time is warped, and the slower time passes relative to regions of weaker gravity. This isn't just a theoretical prediction. It's been confirmed by countless experiments and observations. The first experimental confirmation came from atomic clocks placed at different altitudes. In 1971, physicists Haffel and Keating flew atomic clocks around the world on commercial airliners and compared them to reference clocks on the ground. The flying clocks gained time relative to the ground clocks, exactly as Einstein's theory predicted. Since then, Increasingly precise experiments have confirmed time dilation effects over height differences as small as a few centimeters. The biological implications of this differential aging are fascinating to contemplate, even though the effects are far too small to have any measurable impact on human physiology. Your brain cells are aging slightly faster than the cells in your feet, but the difference accumulates to only nanoseconds over a human lifetime. However, this principle scales dramatically with stronger gravitational fields. Near a black hole, time dilation becomes so extreme that an astronaut's feet, closer to the black hole, would age noticeably slower than their head. This gravitational time dilation has profound implications for our understanding of the universe. It affects everything from the behavior of light climbing out of gravitational wells to the evolution of massive stars. When light travels from a strong gravitational field to a weaker one, it gets redshifted. Its wavelength stretches and its frequency decreases. This gravitational redshift has been observed in light from white dwarf stars and provides another confirmation of Einstein's theory. The effect also plays a crucial role in our understanding of black holes. As matter falls toward a black hole's event horizon, time dilation becomes infinite from the perspective of an outside observer. This means that to someone watching from a safe distance, infalling matter appears to slow down and freeze at the event horizon, with its light redshifting to invisibility. From the perspective of the infalling matter, however, time passes normally, and it crosses the event horizon in finite time, according to its own clocks. In the realm of particle physics, time dilation affects the decay rates of unstable particles. Muons created by cosmic ray collisions high in Earth's atmosphere live longer from our perspective, because they're moving at near light speeds, and time dilation allows them to reach the ground before decaying. Without relativistic effects, most muons would decay long before reaching sea level. The precision required to measure these tiny effects has driven remarkable advances in timekeeping technology. Modern atomic clocks are so precise they can detect height differences of centimeters through gravitational time dilation. These clocks use the vibrations of atoms as their timing mechanism and can maintain accuracy to within 1 second over billions of years. Such precision has opened new avenues for testing fundamental physics and may even lead to practical applications in geology and resource exploration. Consider the philosophical implications of differential aging within your own body. The concept challenges our intuitive notion of time as universal and constant. Every atom in your body experiences time slightly differently depending on its position in Earth's gravitational field. The neurons in your brain, the calcium in your bones, and the iron in your blood are all aging at imperceptibly different rates based on their height above Earth's center. This effect extends beyond individual bodies to entire civilizations. People living at higher altitudes age faster than those at sea level, though again, the differences are far too small to be biologically significant. Mountain dwellers live in regions where time passes faster than for coastal populations. Over the course of human civilization, these differences accumulate to microseconds, but they represent a real, measurable divergence in the passage of time. The technology that makes GPS possible must account for both gravitational time dilation and special relativistic effects from the satellite's high speeds. Without these corrections, GPS accuracy would degrade by several kilometers per day, making the system useless for navigation. Every time you use GPS to find a restaurant or navigate to a destination, you're relying on Einstein's insights about the nature of space and time. As our measurement capabilities continue to improve, we're discovering time dilation effects in increasingly subtle situations. Optical clocks, which use light frequencies rather than microwave frequencies, are approaching precisions where they could detect gravitational time dilation over height differences of just a few millimeters. Such sensitivity could revolutionize our ability to study Earth's gravitational field and might even detect gravitational waves through their effects on the passage of time. Fact 4. Neutron star material weighs 6 billion tons per sugar cube. Neutron stars represent matter compressed to densities so extreme, they challenge our everyday understanding of substance and structure. To comprehend just how dense these cosmic objects are, imagine taking a standard sugar cube, about 1 cubic centimeter in volume, and somehow packing it with neutron star material. That tiny cube would weigh approximately 6 billion tons, roughly equivalent to the mass of Mount Everest, compressed into a space smaller than a dice. This extraordinary density emerges from one of the most violent events in the universe: the collapse of a massive star's core during a supernova explosion. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, gravity overwhelms all other forces, crushing the stellar core in less than a second. The collapse is so rapid and violent that protons and electrons are literally squeezed together to form neutrons, creating a ball of pure nuclear matter typically 12 to 15 kilometers in diameter. To put this collapse in perspective, imagine our Sun, with its diameter of 1.4 million kilometers, compressed down to the size of a small city. The gravitational forces involved are beyond anything we experience on Earth. The escape velocity from a neutron star's surface approaches 1/3 the speed of light, about 100,000 kilometers per second. If you could somehow stand on a neutron star's surface, which you absolutely cannot survive, you would weigh roughly 100 billion times more than you do on Earth. The physics governing neutron star matter pushes the boundaries of our understanding. At these incredible densities, normal atomic structure completely breaks down. The neutrons are packed so tightly that they nearly touch each other, creating what physicists call degenerate matter. This material behaves according to quantum mechanical principles rather than classical physics, with the Pauli exclusion principle, which states that no 2 neutrons can occupy the same quantum state, providing the primary pressure that prevents further collapse. The internal structure of a neutron star is equally remarkable. The outer crust consists of a crystalline lattice of atomic nuclei embedded in a sea of electrons, but as you move deeper, the matter becomes increasingly exotic. In the inner crust, neutrons begin to drip out of atomic nuclei, creating a neutron-rich soup. At the core, conditions become so extreme that physicists speculate about the existence of exotic particles, like hyperons, kaons, or even quark matter, a state where the neutrons themselves break down into their constituent quarks. The magnetic fields of neutron stars add another layer of extremeness to these already incredible objects. Typical neutron stars have magnetic fields trillions of times stronger than Earth's magnetic field, while magnetars, a special class of neutron stars, can have fields up to 1,000 times stronger still. These magnetic fields are so powerful, they would be lethal to any living organism from thousands of kilometers away, not through radiation, but through the direct effects of the magnetic field on biological tissues. The formation process of neutron stars involves energies and forces that dwarf anything humans have created or experienced. During the core collapse that creates a neutron star, the gravitational binding energy released is roughly equivalent to the energy our Sun will produce over its entire 10 billion year lifetime. Most of this energy escapes as neutrinos, ghostly particles that barely interact with matter. But the small fraction that remains creates the spectacular supernova explosion that can outshine an entire galaxy. The study of neutron stars provides unique insights into fundamental physics under conditions impossible to replicate in terrestrial laboratories. These objects serve as natural laboratories for testing theories about matter under extreme conditions, strong gravitational fields, and intense magnetic fields. The recent detection of gravitational waves from neutron star mergers has opened an entirely new window into understanding these exotic objects and their role in cosmic evolution. Neutron stars also serve as cosmic lighthouses through a phenomenon called pulsar emission. As these rapidly rotating neutron stars emit beams of radiation from their magnetic poles, we observe regular pulses as the beams sweep across Earth like lighthouse beams. Some pulsars rotate hundreds of times per second with timing precision that rivals atomic clocks, making them valuable tools for testing Einstein's general relativity and searching for gravitational waves. The implications of neutron star densities extend beyond pure physics into questions about the fundamental nature of matter itself. At what point does matter cease to behave like normal atomic material and become something qualitatively different? Neutron stars may harbor exotic states of matter that exist nowhere else in the universe, providing unique insights into the quantum nature of reality at macroscopic scales. Consider what it would mean to have access to neutron star material. A teaspoon of this matter would weigh more than Mount Everest, but its incredible density would make it gravitationally dangerous. any significant amount of neutron star material would immediately collapse under its own gravity, potentially forming a black hole. The very existence of stable neutron stars represents a delicate balance between gravitational collapse and quantum pressure that defines one of nature's most extreme stable configurations. The temperature of newly formed neutron stars reaches billions of degrees, hot enough to emit primarily in X-rays and gamma rays. Over millions of years, they cool through neutrino emission and thermal radiation. But even old neutron stars maintain surface temperatures of millions of degrees. This thermal emission, combined with their small size, makes neutron stars extremely difficult to observe, except through their interactions with companion stars, or their emission as pulsars. Recent observations have revealed that neutron stars are not perfectly smooth spheres, but can have mountains on their surfaces. These mountains are only centimeters high due to the intense gravitational field, but they represent enormous concentrations of matter. The formation and evolution of these surface features may be related to the star's magnetic field evolution and could be sources of continuous gravitational waves as the star rotates. The study of neutron stars continues to reveal new mysteries. Some neutron stars appear to have surfaces composed of exotic crystalline structures, while others show evidence of superfluidity in their cores. The recent detection of neutron star mergers through gravitational waves has confirmed that these collisions are major sources of heavy elements like gold and platinum, fundamentally changing our understanding of how the universe's chemical elements are created and distributed. Fact 5. 95% of the universe is invisible dark matter and dark energy. One of the most humbling discoveries in modern cosmology is that everything we can see, touch, and directly detect, all the stars, planets, galaxies, and cosmic gas, represents only about 5% of the universe's total content. The remaining 95% consists of two mysterious components that we can neither see nor directly interact with: dark matter and dark energy. This revelation fundamentally challenges our understanding of the cosmos and our place within it. Dark matter comprises approximately 27% of the universe's mass-energy content. Despite being invisible to our telescopes, we know it exists through its gravitational effects on visible matter. Galaxies rotate faster than they should based on their visible mass alone. Galaxy clusters move in ways that require more matter than we can observe. And the cosmic microwave background radiation shows patterns that only make sense if dark matter existed in the early universe. Yet despite decades of increasingly sophisticated experiments, we have never directly detected a single dark matter particle. The evidence for dark matter spans multiple scales and observations. In individual galaxies, stars in the outer regions orbit at speeds that would cause them to fly away, if only the visible matter provided the gravitational binding. The rotation curves of spiral galaxies remain flat far beyond where most visible matter ends, indicating the presence of extended dark matter halos. Gravitational lensing observations show that massive galaxy clusters bend light from background objects more than their visible mass alone could account for, revealing the gravitational signature of invisible matter. Dark energy is even more mysterious, comprising approximately 68% of the universe. Discovered through observations of distant supernovae in the late 1990s, dark energy appears to be causing the expansion of the universe to accelerate. This discovery was so unexpected that astronomers initially suspected experimental error. The universe should be slowing down its expansion due to the gravitational attraction between all the matter it contains, but instead, it's speeding up. The nature of dark energy remains one of the greatest mysteries in modern physics. It could be a property of space itself, a cosmological constant that Einstein once proposed and later called his greatest mistake. Alternatively, it might be a dynamic field that changes over time, similar to the inflaton field thought to have driven cosmic inflation in the universe's first moments. Some theories suggest dark energy might not exist at all, and our observations might indicate a need to modify our understanding of gravity on cosmic scales. The cosmic timeline reveals the changing balance between these invisible components. In the early universe, matter dominated, but as expansion continued and matter density decreased, dark energy's influence grew. About 5 billion years ago, dark energy overtook matter as the dominant component, initiating the current epoch of accelerated expansion. This transition coincidentally occurred around the time our solar system formed, highlighting our existence during a unique phase of cosmic evolution. The search for dark matter has spawned some of the most sensitive physics experiments ever devised. Deep underground laboratories shield detectors from cosmic rays while they wait for the rare collision between a dark matter particle and atomic nuclei. Particle accelerators attempt to create dark matter particles through high-energy collisions, while space-based telescopes search for the gamma rays that might result from dark matter annihilation. Despite these efforts, dark matter remains frustratingly elusive. Leading candidates for dark matter include weakly interacting massive particles, or WIMPs, which interact only through gravity and the weak nuclear force. Other possibilities include axions, extremely light particles proposed to solve certain problems in particle physics, or sterile neutrinos that barely interact with ordinary matter. Some theories suggest dark matter might consist of primordial black holes formed in the early universe, though observations have ruled out many mass ranges for such objects. The distribution of dark matter shapes the large-scale structure of the universe. Computer simulations show that dark matter forms a cosmic web of filaments and nodes, with ordinary matter following these invisible scaffolds. Galaxies form at the intersections of dark matter filaments, while vast cosmic voids contain little matter of any kind. The cosmic web structure, visible in galaxy surveys, matches predictions based on dark matter physics remarkably well. Dark energy's properties remain largely unknown, but its effects are becoming increasingly apparent. As the universe continues to expand and accelerate, galaxies beyond our local group will eventually disappear beyond our cosmic horizon. In the far future, dark energy may lead to a Big Rip scenario, where the acceleration becomes so extreme that it overcomes all other forces, tearing apart galaxies, stars, and eventually atoms themselves. The philosophical implications of dark matter and dark energy are profound. We live in a universe where the vast majority of its contents remain completely unknown to us. This invisible cosmos influences everything we observe, from the formation of the first stars to the ultimate fate of the universe. Yet we can only infer its existence through its effects on the small fraction of matter we can see. Recent observations have provided new clues about these mysterious components. The Planck satellite's precise measurements of the cosmic microwave background have refined our estimates of dark matter and dark energy densities. Large galaxy surveys map the three-dimensional distribution of matter across billions of light years, revealing how dark matter clustering evolves over cosmic time. Gravitational wave detectors might eventually sense the effects of dark matter on the propagation of space-time ripples. The study of dark matter and dark energy represents one of the most active frontiers in modern physics and astronomy. New theories propose connections between these invisible components, suggesting they might be different manifestations of the same underlying physics. Other theories question whether dark matter and dark energy exist at all, proposing modifications to Einstein's general relativity that could explain observations without invoking new forms of matter and energy. Understanding dark matter and dark energy may require revolutionary advances in fundamental physics, comparable to the discoveries of quantum mechanics and relativity in the 20th century. These invisible components might hold keys to unifying gravity with the other fundamental forces, understanding the nature of space and time, or revealing the existence of extra dimensions. The fact that 95% of the universe remains mysterious reminds us that despite our scientific progress, we have only begun to comprehend the cosmos we inhabit. Fact 6. The universe has no center or edge. One of the most counterintuitive concepts in cosmology is that the universe, despite having begun with the Big Bang, has no center and no edge. This idea challenges our everyday experience, where every explosion has a center, every object has boundaries, and every expansion occurs into pre-existing space. Understanding why the universe lacks these familiar features requires us to fundamentally reconsider the nature of space, time, and cosmic expansion. The confusion often arises from visualizing the Big Bang as an explosion that occurred at a specific point in pre-existing space, sending matter and energy outward in all directions. This visualization is fundamentally incorrect. The Big Bang was not an explosion in space, but rather an explosion of space itself. Space, time, and all the matter and energy in the universe came into existence simultaneously at the moment of the Big Bang. There was no pre-existing space for the universe to expand into, and there was no central point from which the expansion began. To understand this concept, cosmologists often use the analogy of an inflating balloon. Imagine drawing dots on the surface of a balloon to represent galaxies, then inflating the balloon. As the balloon expands, every dot moves away from every other dot, but there is no center to this expansion on the balloon's surface. Any observer on any dot would see all other dots moving away and would conclude that they are at the center of the expansion. This is precisely what we observe in our universe. Every galaxy appears to be moving away from us, but this doesn't mean we're at the center. The balloon analogy has limitations, however. The balloon has a center in the three-dimensional space that contains it, but the universe as a whole has no such containing space. The universe is all there is. It doesn't exist within something larger. When cosmologists say the universe is expanding, they mean that the distances between galaxies are increasing, not that the universe is growing into pre-existing empty space. Einstein's theory of general relativity provides the mathematical framework for understanding this expansion. The theory describes how space and time form a unified space-time continuum that can be curved and distorted by matter and energy. The expansion of the universe is described by the stretching of space-time itself. As space expands, it carries galaxies along with it, like raisins in rising bread dough. The galaxies themselves aren't moving through space at high speeds. Rather, space is expanding between them. The concept of the universe having no edge is equally challenging to visualize. In our daily experience, every object has boundaries: the edge of a table, the surface of a ball, the borders of a country. But the universe, being everything that exists, cannot have an edge in the conventional sense. If it had an edge, what would be beyond that edge? More space? Nothing at all. Both concepts lead to logical contradictions when applied to the totality of existence. Current observations are consistent with the universe being either infinite in size or finite, but without boundaries, like the surface of a sphere. If the universe is infinite, it has always been infinite, even at the moment of the Big Bang. The Big Bang represents the beginning of time and the moment when the universe began expanding from an infinitely dense state, not the creation of space from nothing. If the universe is finite, it likely has a spherical or hyperbolic geometry that curves back on itself, having no edges, just as the surface of a sphere has no boundaries. The observable universe, however, does have a boundary: the cosmic horizon. This represents the farthest distance from which light has had time to reach us since the Big Bang. Currently, we can observe objects approximately 46 billion light-years away in any direction, even though the universe is only about 13.8 billion years old. This apparent contradiction arises because space itself has been expanding during the time light has been traveling from distant objects. The cosmic horizon is not a physical boundary, but rather a limitation imposed by the finite age of the universe and the finite speed of light. Beyond this horizon lie regions of the universe that we cannot observe because light from those regions hasn't had enough time to reach us yet. As time passes, our observable universe grows larger, as light from increasingly distant regions arrives at Earth. The homogeneity and isotropy of the universe provide strong evidence for the lack of a center. On large scales, the universe looks essentially the same in all directions from any vantage point. This cosmic principle, supported by observations of the cosmic microwave background radiation and large-scale galaxy surveys, would be impossible if the universe had a special central location. The uniformity of the cosmic microwave background, with temperature variations of only a few parts per million, indicates that the early universe was remarkably homogeneous. Understanding the universe's lack of center and edge has profound implications for cosmology and our place within it. It means that no location in the universe is special or privileged, a principle that extends back to Copernicus's realization that Earth is not the center of the solar system. Every observer in the universe sees the same large-scale pattern of cosmic expansion, with distant galaxies receding at speeds proportional to their distance. The expansion of space also affects our understanding of distance and time in cosmology. When we observe distant galaxies, we see them as they were billions of years ago, because light takes time to travel across cosmic distances. The galaxy we observe at a distance of 10 billion light-years appears as it was 10 billion years ago. But due to cosmic expansion, that galaxy is now much farther away from us than 10 billion light-years. This expansion has practical consequences for the ultimate fate of the universe. If the expansion continues to accelerate, as current observations suggest, galaxies beyond our local group will eventually disappear beyond our cosmic horizon. Future astronomers will live in an apparently much smaller and lonelier universe, unable to observe the cosmic microwave background or distant galaxies that provide evidence for the Big Bang and cosmic evolution. The concept that the universe has no center or edge also challenges our intuitions about causality and communication across cosmic distances. Information cannot travel faster than the speed of light, which means that widely separated regions of the universe cannot influence each other instantaneously. This leads to the horizon problem in cosmology, the question of how the universe achieved such remarkable homogeneity when distant regions could never have been in causal contact. Recent theoretical developments, including the theory of cosmic inflation, propose that the early universe underwent a period of exponential expansion that stretched quantum fluctuations to cosmic scales. This inflation could explain the universe's homogeneity and provide the seeds for the large-scale structure we observe today. However, inflation also suggests that the universe is likely infinite and contains regions with different physical properties, leading to the concept of a multiverse where our observable universe is just one small part of a vast and varied cosmos. Fact 7. Time moves slower in stronger gravitational fields. The relationship between gravity and time represents one of Einstein's most profound insights into the nature of reality. Gravitational time dilation reveals that time is not the constant, universal flow we experience in daily life, but rather a dimension that can be stretched and compressed by the presence of mass and energy. In stronger gravitational fields, time literally moves slower relative to regions of weaker gravity, an effect that has been precisely measured and has profound implications for our understanding of the universe. This phenomenon emerges from Einstein's principle of equivalence, which states that acceleration and gravity are indistinguishable from each other. If you're in an elevator accelerating upward, you can't tell the difference between that acceleration and the pull of gravity. This insight led Einstein to realize that gravity isn't a force in the traditional sense, but rather a curvature in the fabric of space-time itself. Massive objects warp space-time, and this warping affects the passage of time. The mathematics behind gravitational time dilation shows that time dilation increases with gravitational potential. The stronger the gravitational field, the more pronounced the effect. Near a massive object like Earth, time runs slower than it does in the weaker gravitational field of outer space. The effect becomes dramatic near extremely massive objects like neutron stars and black holes, where gravitational fields can be billions of times stronger than Earth's. Experimental verification of gravitational time dilation began with the Pound-Rebka experiment in 1959. Physicists Robert Pound and Glenn Rebka used gamma rays to measure the tiny frequency shifts caused by Earth's gravitational field over a height difference of just 22.5 meters in a Harvard University tower. The gamma rays lost energy climbing against gravity, causing their frequency to decrease in precise agreement with Einstein's predictions. Since then, increasingly sensitive experiments have confirmed gravitational time dilation with extraordinary precision. Atomic clocks taken to different altitudes show measurable differences in their tick rates. A clock at the top of a skyscraper runs faster than an identical clock at ground level. The difference is minuscule, only nanoseconds over years of operation, but it's real and measurable with modern atomic clock technology. The Global Positioning System provides a dramatic real-world example of gravitational time dilation's practical importance. GPS satellites orbit at an altitude of approximately 20,000 kilometers, where Earth's gravitational field is significantly weaker than at the surface. Without corrections for gravitational time dilation, GPS would accumulate errors of several kilometers per day, making the system completely useless for navigation. The GPS system must account for two relativistic effects: gravitational time dilation and special relativistic time dilation from the satellite's orbital velocity. The gravitational effect causes satellite clocks to run about 45 microseconds per day faster than ground clocks, while the velocity effect causes them to run about 7 microseconds per day slower. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. To understand the physical mechanism behind gravitational time dilation, consider how light behaves in gravitational fields. When light travels from a region of strong gravity to a region of weak gravity, it loses energy and becomes redshifted. Its wavelength increases and its frequency decreases. Since the frequency of light can serve as a clock, this redshift represents the slowing of time in stronger gravitational fields. Conversely, light falling into a gravitational well becomes blue shifted, representing the speeding up of time as seen from the stronger field. The effect becomes extreme near black holes, where gravitational time dilation approaches infinity at the event horizon. From the perspective of a distant observer, time appears to slow to a crawl for objects approaching a black hole. An astronaut falling toward a black hole would appear to slow down and eventually freeze at the event horizon, their image redshifted beyond visibility. From the astronaut's perspective, however, their own clocks would tick normally, and they would cross the event horizon in finite proper time. Gravitational time dilation also affects stellar evolution and the aging of the universe itself. In the cores of massive stars, where gravitational fields are intense, nuclear fusion processes occur more slowly from the perspective of distant observers. This affects stellar lifetimes and the production of heavy elements. Time dilation in strong gravitational fields influences the collapse of massive stars and the formation of neutron stars and black holes. The phenomenon has implications for our understanding of the early universe. In the first moments after the Big Bang, when the universe was extremely dense, gravitational time dilation would have been significant throughout space. The expansion of the universe and the decrease in density reduced these effects over cosmic time. Understanding these early conditions requires careful consideration of how time dilation affected physical processes in the primordial cosmos. White dwarf stars provide another laboratory for studying gravitational time dilation. These dense stellar remnants have surface gravitational fields thousands of times stronger than Earth's. Light from white dwarfs shows measurable gravitational redshift, confirming Einstein's predictions for intermediate strength gravitational fields. The redshift allows astronomers to measure the mass and gravitational field strength of these distant objects. Modern atomic clocks have become so precise that they can detect gravitational time dilation over height differences of just centimeters. Optical atomic clocks, which use light frequencies rather than microwave frequencies as their reference, can measure time dilation effects that would arise from moving the clock up or down by distances smaller than the width of this page. This precision opens new possibilities for testing fundamental physics and even practical applications in geodesy and geology. The relationship between gravity and time also affects the synchronization of clocks across Earth's surface. Clocks at different altitudes and in regions of different gravitational field strength naturally drift apart over time. Maintaining a global time standard requires careful accounting for these gravitational effects. The International Atomic Time Standard incorporates corrections for gravitational time dilation to maintain coherent timekeeping worldwide. Gravitational time dilation plays a role in gravitational wave detection. When gravitational waves pass through space, they alternately stretch and compress distances, effectively modulating the local gravitational field. This modulation causes tiny changes in the rate at which time passes, which can be detected by comparing the round-trip light travel times in the arms of laser interferometer gravitational wave observatories like LIGO and Virgo. The effect also influences our understanding of cosmological redshift. Light from distant galaxies is redshifted not only by the expansion of the universe, but also by the gravitational fields it encounters along its journey. Light climbing out of galaxy clusters and passing near massive objects experiences additional redshift beyond that caused by cosmic expansion. This gravitational contribution must be accounted for in precise cosmological measurements. Gravitational time dilation reveals the deep connection between space, time, matter, and energy that lies at the heart of general relativity. It shows that time is not an absolute backdrop against which physical events unfold, but rather a dynamical quantity. that responds to the distribution of mass and energy in the universe. This insight has revolutionized our understanding of everything from the GPS satellites overhead to the black holes at the centers of galaxies, demonstrating once again that the universe operates according to principles far stranger and more wonderful than our everyday intuition might suggest. Fact 8. Some planets rain diamonds. In the depths of our solar system's ice giants, Neptune and Uranus, conditions exist that would create one of the most valuable weather phenomena imaginable on Earth: diamond rain. These distant worlds harbor atmospheric pressures and temperatures so extreme that they transform simple carbon-containing compounds into crystalline diamonds that literally precipitate through the planet's dense atmospheres like a cosmic treasure storm. The process begins in the upper atmospheres of these ice giants, where methane molecules exist in abundance. Neptune and Uranus contain approximately 2 to 3% methane in their atmospheres, mixed with hydrogen and helium. When exposed to the intense heat and pressure conditions deeper within these planets, the methane undergoes chemical decomposition. The extreme conditions, pressures millions of times greater than Earth's atmospheric pressure and temperatures reaching thousands of degrees Celsius, break apart the methane molecules, separating carbon from hydrogen. Under these extraordinary conditions, carbon atoms reorganize themselves into the crystalline structure we recognize as diamond. The process requires pressures exceeding 200,000 times Earth's atmospheric pressure and temperatures above 2,000 degrees Celsius. These conditions exist naturally within the interior regions of Neptune and Uranus, approximately 7,000 kilometers below their cloud tops, where the atmospheric density approaches that of liquid water, but with far greater pressures. Laboratory experiments have confirmed the theoretical predictions about diamond formation in ice giant atmospheres. Scientists have used powerful lasers to recreate the extreme pressures and temperatures found within Neptune and Uranus, subjecting samples of hydrocarbon compounds to conditions that mimic planetary interiors. These experiments successfully produced microscopic diamonds, validating the theoretical models that predict diamond rain on ice giants. The diamonds formed in these planetary atmospheres wouldn't resemble the clear, brilliant gems prized on Earth. Instead, they would likely be small, dark crystals mixed with other carbon compounds and planetary materials. The continuous formation and reformation of these diamonds in the dynamic atmospheric conditions would create a constant cycle of crystallization and dissolution, with diamonds growing and shrinking as they move through different pressure and temperature zones. The scale of diamond production on these planets is truly astronomical. Estimates suggest that thousands of tons of diamonds could be raining through the atmospheres of Neptune and Uranus at any given time. Over the planet's 4.5 billion year histories, the total amount of diamonds produced could measure in the millions of tons. These diamonds would eventually settle toward the planetary cores, potentially forming diamond oceans or diamond-rich layers within the planet's complex interior structures. The discovery of diamond rain has implications beyond simple scientific curiosity. Understanding how diamonds form under extreme conditions provides insights into high-pressure physics and chemistry that have applications in materials science and industrial processes. The extreme conditions that create diamonds in planetary atmospheres help scientists understand similar processes that might occur in other extreme environments throughout the universe. Other planets and moons throughout the solar system might harbor different types of exotic precipitation. Venus's surface temperatures and atmospheric composition could potentially support sulfuric acid rain, while Titan, Saturn's largest moon, experiences methane and ethane precipitation in its hydrocarbon cycle. These exotic weather systems remind us that planetary atmospheres can create conditions far beyond anything experienced on Earth. The formation of diamonds in planetary atmospheres also relates to our understanding of planetary formation and evolution. The ice giants likely formed farther from the Sun than their current positions, migrating inward over millions of years through gravitational interactions with other planets and the protoplanetary disk. This migration history affects their internal structure and the conditions that enable diamond formation. Recent research has extended the diamond rain concept to exoplanets, planets orbiting other stars. Many discovered exoplanets are larger than Neptune and Uranus, with even more extreme atmospheric conditions. super Neptunes and other types of massive planets might experience diamond rain on scales that dwarf what occurs in our solar system. Some exoplanets orbit so close to their stars that their entire atmospheres exist under extreme pressure and temperature conditions favorable for diamond formation. The study of diamond rain also connects to broader questions about carbon chemistry in planetary environments. Carbon is the fourth most abundant element in the universe and forms the basis for all known life. Understanding how carbon behaves under extreme conditions helps scientists predict the types of chemistry that might occur on planets throughout the galaxy, including the formation of complex organic compounds that could serve as precursors to biological molecules. The diamonds raining through ice giant atmospheres would experience a journey unlike anything on Earth. Starting as methane molecules in the upper atmosphere, they would decompose under increasing pressure and temperature, crystallize into diamond form, and then potentially dissolve or transform again as they continue their descent through the dynamic atmospheric layers. This constant cycle of formation and transformation represents one of nature's most exotic material recycling systems. The economic implications of planetary diamond rain capture the imagination, even though harvesting these extraterrestrial gems remains far beyond current technology. The diamonds on Neptune and Uranus exist under conditions that would instantly destroy any spacecraft we could currently build. Even if we could somehow access these diamonds, the cost of space missions to the outer solar system would far exceed the value of any diamonds we could retrieve. The discovery of diamond rain exemplifies how the universe continually surprises us with phenomena that challenge our Earth-based expectations. What seems impossible or purely fictional, diamonds falling from the sky, turns out to be a natural consequence of physics and chemistry under conditions that exist commonly throughout the cosmos. The ice giants in our own solar system host weather patterns more exotic than the wildest science fiction, reminding us that reality often exceeds imagination. Understanding diamond rain also provides insights into the internal structure and dynamics of ice giant planets. The movement of diamonds through planetary atmospheres affects heat transport and atmospheric circulation patterns. These processes influence the planet's overall energy balance and contribute to the complex atmospheric dynamics that we observe telescopically from Earth. The research into planetary diamond rain continues to evolve as our understanding of extreme chemistry and physics advances. New theoretical models and laboratory experiments refine our predictions about where and how diamonds form in planetary atmospheres. Future space missions to the ice giants could provide direct measurements of atmospheric composition and structure that would further validate or refine our understanding of these exotic precipitation processes. The phenomenon of diamond rain illustrates the incredible diversity of physical and chemical processes occurring throughout the universe. From the perspective of cosmic chemistry, the formation of diamonds in planetary atmospheres represents just one example of how extreme conditions can transform ordinary materials into extraordinary substances. Each planet and moon in our solar system hosts unique combinations of pressure, temperature, and chemical composition that create their own distinctive geological and atmospheric processes, many of which remain to be discovered and understood. Fact 9. Empty space is filled with quantum particle pairs. One of the most counterintuitive discoveries in modern physics is that what we call empty space, the vacuum of space itself, is actually teeming with activity at the quantum level. The quantum vacuum is not empty at all, but rather filled with constantly fluctuating fields that spontaneously create pairs of virtual particles, which exist for infinitesimally brief moments before annihilating each other and disappearing back into the vacuum. This quantum foam represents the fundamental graininess of space-time itself at the smallest possible scales. The concept emerges from Heisenberg's uncertainty principle, one of the cornerstone principles of quantum mechanics. This principle states that there are fundamental limits to how precisely we can simultaneously know certain pairs of properties, such as position and momentum, or energy and time. The energy-time uncertainty relation allows for the temporary borrowing of energy from the vacuum to create particle pairs, as long as this energy is paid back within an extremely short time determined by the uncertainty principle. These virtual particle pairs consist of a particle and its antiparticle, for example, an electron and a positron, or a photon and an antiphoton. They spring into existence throughout all of space, existing for periods so brief that they cannot be directly observed or measured. The more massive the particle pair, the shorter their allowed existence time. A virtual electron-positron pair might exist for approximately 10 to the negative 21st seconds, while virtual proton-antiproton pairs exist for only about 10 to the negative 24th seconds. The quantum vacuum's energy density is truly staggering when calculated naively. If we simply add up all the possible quantum fluctuations across all frequencies and particle types, the energy density of empty space would be enormous, far greater than the energy density of the most massive stars. This calculation leads to what physicists call the cosmological constant problem, one of the most significant unsolved problems in theoretical physics. The observed vacuum energy density of our universe is approximately 10 to the power of 120 times smaller than theoretical predictions suggest it should be. Despite this theoretical puzzle, quantum vacuum fluctuations produce measurable effects that have been confirmed experimentally. The Casimir effect represents one of the most famous demonstrations of quantum vacuum reality. When two uncharged metal plates are placed extremely close together in a vacuum, they experience an attractive force that pushes them toward each other. This force arises because the quantum vacuum fluctuations between the plates are restricted compared to the fluctuations in the open space outside the plates, creating a measurable pressure difference. The Casimir effect has been precisely measured in numerous laboratory experiments, confirming the predictions of quantum field theory with extraordinary accuracy. The force is incredibly weak, equivalent to the pressure exerted by light from a small flashlight, but it's detectable with sensitive instruments. This effect has practical implications for nanotechnology and microelectromechanical systems, where surfaces can be brought close enough together that Casimir forces become significant. Quantum vacuum fluctuations also affect the behavior of atoms and their interaction with electromagnetic fields. The Lamb shift discovered in hydrogen atoms represents a tiny energy difference between electron orbital levels that can only be explained by the atom's interaction with quantum vacuum fluctuations. This effect has been measured with incredible precision and provides one of the most stringent tests of quantum electrodynamics, the theory describing how light and matter interact. The quantum vacuum plays a crucial role in our understanding of fundamental particle physics. Virtual particles mediate all fundamental forces in nature. The electromagnetic force between charged particles is carried by virtual photons. The strong nuclear force is carried by virtual gluons, and the weak nuclear force is carried by virtual W and Z bosons. Even gravity, according to quantum field theories of gravity, would be mediated by virtual gravitons. These virtual particles are not directly observable, but are essential to understanding how forces operate at the quantum level. Hawking radiation provides another fascinating connection between quantum vacuum fluctuations and observable physics. Near the event horizon of a black hole, virtual particle pairs can become separated, with one particle falling into the black hole while the other escapes as real radiation. This process causes black holes to slowly evaporate over astronomical timescales, with smaller black holes evaporating faster than larger ones. The Hawking radiation temperature is inversely proportional to the black hole's mass, meaning stellar mass black holes are incredibly cold, while microscopic black holes would be extremely hot. The concept of quantum vacuum fluctuations has implications for our understanding of the early universe. During the inflationary epoch, quantum fluctuations in the vacuum were stretched to cosmic scales by the rapid expansion of space-time. These quantum fluctuations became the seeds for the large-scale structure we observe in today's universe, the slight density variations that eventually grew into galaxies and galaxy clusters through gravitational attraction. Modern quantum field theory describes the vacuum as the ground state of quantum fields that permeate all of space. Even in this lowest energy state, the fields retain zero-point energy due to quantum mechanical constraints. This zero-point energy represents the minimum possible energy that quantum systems can possess, and it exists even at absolute zero temperature, when all thermal motion has ceased. The quantum vacuum also affects the properties of particles and atoms. Quantum electrodynamics predicts that the vacuum polarization, the creation and annihilation of virtual electron-positron pairs, slightly modifies the electromagnetic field around charged particles. This effect has been measured with extraordinary precision, and represents one of the most accurate confirmations of quantum field theory predictions. Recent theoretical developments have explored connections between quantum vacuum fluctuations and dark energy, the mysterious component that appears to be accelerating the universe's expansion. Some theories propose that the quantum vacuum energy might contribute to dark energy, though reconciling the theoretical and observed values remains one of the most challenging problems in physics. Alternative approaches suggest that quantum vacuum fluctuations might have different properties in curved spacetime or at cosmic scales. The study of quantum vacuum fluctuations has practical applications in emerging technologies. Quantum computing relies on manipulating quantum states that exist against the background of vacuum fluctuations. Understanding and controlling these fluctuations is crucial for maintaining quantum coherence in quantum computers and other quantum devices. The development of quantum sensors and quantum communication systems must account for the effects of vacuum fluctuations on their operation. The quantum vacuum also plays a role in high-energy particle physics experiments. Particle accelerators can convert virtual particles into real particles by providing sufficient energy to make the quantum fluctuations permanent. The discovery of new particles often involves understanding how they couple to the quantum vacuum and how vacuum fluctuations affect particle interactions at high energies. The philosophical implications of quantum vacuum fluctuations challenge our classical notions of emptiness and nothingness. The quantum vacuum reveals that even the absence of matter and radiation represents a dynamic, fluctuating medium filled with constant activity. This insight suggests that the most fundamental level of physical reality involves continuous creation and destruction of virtual particles, making the vacuum a rich and complex arena for physical phenomena. Future research into quantum vacuum properties may reveal new physics beyond the standard model of particle physics. Experiments designed to probe vacuum fluctuations at increasingly sensitive levels might detect signatures of extra dimensions, supersymmetric particles, or other exotic phenomena predicted by advanced theoretical frameworks. The quantum vacuum remains one of the most active frontiers in fundamental physics research, promising continued surprises and insights into the deepest levels of natural reality. Fact 10. Gamma-ray bursts outshine entire galaxies. Gamma-ray bursts represent the most energetic explosive events in the universe since the Big Bang itself. These cosmic phenomena release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime, and they can briefly outshine entire galaxies containing hundreds of billions of stars. When a gamma-ray burst occurs, it becomes the brightest source of gamma radiation in the observable universe, visible across billions of light years of space and detectable by our most sensitive instruments. The discovery of gamma-ray bursts occurred by accident during the Cold War era. In the late 1960s, the United States launched a series of military satellites designed to monitor compliance with nuclear test ban treaties by detecting gamma rays from nuclear explosions. Instead of catching treaty violations, these satellites began detecting intense bursts of gamma rays coming from space. The phenomenon was so unexpected that it took years for scientists to convince themselves that these signals were truly astronomical in origin, rather than equipment malfunctions or terrestrial interference. Gamma-ray bursts fall into two main categories based on their duration and spectral characteristics. Short gamma-ray bursts last less than 2 seconds and appear to result from the collision of two neutron stars, or a neutron star and a black hole. Long gamma-ray bursts can last from several seconds to several minutes and are associated with the collapse of extremely massive stars, hypernovae that mark the death of stars more than 25 times the mass of our Sun. Both types involve the formation or merger of compact objects under the most extreme conditions imaginable. The energy released during a gamma-ray burst is almost incomprehensible. A typical burst releases approximately 10 to the 44th joules of energy in gamma rays alone, equivalent to the mass energy of several suns completely converted to pure energy, according to Einstein's famous equation E equals mc squared. This energy is focused into narrow jets beamed along the rotation axis of the collapsed star or merged compact objects, concentrating the emission into solid angles of only a few degrees. The beaming effect explains how gamma-ray bursts can appear so luminous despite their enormous distances. If the energy were emitted isotropically in all directions, the required energy output would exceed the total mass energy of the most massive stars. Instead, the energy is concentrated into narrow cones, typically with opening angles of a few degrees to a few tens of degrees. We only observe gamma-ray bursts when one of these jets happens to point directly toward Earth, suggesting that many more gamma-ray bursts occur throughout the universe, but remain undetected because their jets point in other directions. The afterglow phenomenon provides crucial insights into gamma-ray burst physics. After the initial burst of gamma rays, the explosion continues to emit radiation at lower energies, X-rays, optical light, and radio waves, for days, months, or even years. This afterglow occurs as the relativistic jet plows into the surrounding interstellar medium, creating shock waves that accelerate particles to enormous energies and produce synchrotron radiation across the electromagnetic spectrum. The jets from gamma-ray bursts move at velocities extremely close to the speed of light, typically 99.9% of light speed or higher. This creates relativistic effects that compress the timescales and frequencies of the observed radiation. The material in the jet experiences time dilation and length contraction, while the radiation is Doppler boosted toward higher frequencies due to the jet's motion towards the observer. These relativistic effects are essential for understanding the observed properties of gamma-ray bursts. The progenitor systems that create gamma-ray bursts represent some of the most extreme stellar evolutionary endpoints. For long bursts, the progenitor stars must be extremely massive, rapidly rotating, and have low metallicity, meaning they contain relatively few heavy elements. These conditions favor the formation of rapidly spinning black holes surrounded by accretion disks, the configuration necessary to launch powerful relativistic jets. The rarity of stars meeting these criteria explains why gamma-ray bursts are relatively uncommon events. Short gamma-ray bursts arise from neutron star mergers, events that have gained enormous attention following the detection of gravitational waves from such mergers by LIGO and Virgo detectors. The collision of two neutron stars creates conditions of extreme density and magnetic field strength that can power relativistic jets while simultaneously producing heavy elements through rapid neutron capture processes. These mergers are now recognized as major sources of gold, platinum, and other heavy elements in the universe. The detection and study of gamma-ray bursts require sophisticated space-based observatories. Earth's atmosphere absorbs gamma rays, making ground-based detection impossible. Satellites like the Fermi Gamma Ray Space Telescope and the Swift Observatory continuously monitor the sky for gamma-ray bursts, automatically alerting ground-based telescopes to begin follow-up observations of the afterglows. This rapid response capability has revolutionized our understanding of these phenomena. The cosmological distances of gamma-ray bursts make them valuable probes of the early universe. Some gamma-ray bursts have been detected at redshifts corresponding to when the universe was less than 1 billion years old, providing information about star formation and stellar evolution in the cosmic dawn era. The most distant gamma-ray bursts serve as lighthouses that illuminate the intervening intergalactic medium, allowing astronomers to study the chemical evolution and ionization state of the early universe. The potential danger posed by gamma-ray bursts to life on Earth has been the subject of scientific speculation and research. If a gamma-ray burst occurred within our galaxy and its jet pointed toward Earth, the intense radiation could potentially damage our atmosphere's ozone layer, leading to increased ultraviolet radiation reaching the surface. Some researchers have proposed that gamma-ray bursts might be responsible for past mass extinction events, though definitive evidence for such connections remains elusive. The study of gamma-ray bursts has led to advances in relativistic astrophysics and plasma physics. Understanding how relativistic jets are launched and maintained requires sophisticated theoretical modeling and numerical simulations. The extreme conditions in gamma-ray burst engines, with magnetic fields trillions of times stronger than Earth's and matter densities comparable to atomic nuclei, push theoretical physics to its limits and provide natural laboratories for testing our understanding of fundamental physical processes. Recent observations have revealed the diversity within gamma-ray burst populations. Some bursts show evidence for multiple jet components with different properties, while others exhibit unusual spectral characteristics that challenge standard models. The discovery of very high-energy gamma rays from some bursts, detected hours or days after the initial explosion, suggests complex and long-lasting particle acceleration processes that extend far beyond the prompt emission phase. The connection between gamma-ray bursts and the formation of stellar mass black holes provides insights into one of the most violent processes in stellar evolution. The collapse of a massive star's core to form a black hole must overcome enormous pressures and magnetic fields while maintaining sufficient rotation to power a relativistic jet. Understanding this process helps explain how the most massive stars end their lives and how stellar mass black holes acquire their properties. Future gamma-ray burst research will benefit from next-generation observatories across the electromagnetic spectrum. Space-based gamma-ray telescopes, with improved sensitivity and temporal resolution, will detect fainter and more distant bursts, while ground-based gravitational wave detectors will increasingly identify the neutron star mergers that produce short bursts. The combination of electromagnetic and gravitational wave observations promises to provide unprecedented insights into these most energetic phenomena in the universe. The legacy of gamma-ray burst research extends beyond astrophysics to fundamental physics and cosmology. These events provide natural particle accelerators that achieve energies far beyond anything possible in terrestrial laboratories, offering opportunities to test theories of particle physics under extreme conditions. As we continue to study these cosmic explosions, gamma-ray bursts will undoubtedly reveal new insights into the nature of matter, energy, and space-time itself at the most extreme limits of physical reality. Fact 11. You are made of atoms forged inside dying stars. Perhaps no fact about the universe is more poetic or profound than the realization that every atom in your body, except for hydrogen, was created in the nuclear furnace of a dying star. The calcium in your bones, the iron in your blood, the oxygen you breathe, and the carbon that forms the backbone of your DNA, all were forged in stellar cores under temperatures and pressures so extreme they dwarf anything found on Earth. You are quite literally made of star stuff, connected to the cosmos in the most fundamental way imaginable. This extraordinary story begins with the Big Bang, which occurred approximately 13.8 billion years ago. In those first moments, the universe was so hot and dense that only the lightest elements could form: hydrogen, helium, and trace amounts of lithium. Everything else, every element heavier than lithium that exists in the universe today, had to be created later through nuclear processes inside stars. The primordial universe was a much simpler place, lacking the chemical diversity necessary for planets, life, or the complex chemistry that drives biological processes. The first generation of stars, called Population 3 stars, formed from this primordial gas composed almost entirely of hydrogen and helium. These ancient stars were likely much more massive than typical stars today, perhaps 50 to several hundred times the mass of our Sun. Their enormous mass meant they burned through their nuclear fuel rapidly, living for only a few million years before exhausting their hydrogen and helium supplies. As they approached the end of their lives, these stellar giants began the process of creating heavier elements through nuclear fusion. Nuclear fusion in stellar cores operates through a series of increasingly complex processes as stars age. Initially, stars convert hydrogen into helium through the proton-proton chain, or the carbon-nitrogen-oxygen cycle. This process releases enormous amounts of energy and allows stars to shine for billions of years. However, when the hydrogen in the core is exhausted, the star must find new sources of nuclear fuel to continue generating the energy needed to support itself against gravitational collapse. As hydrogen becomes scarce in the stellar core, helium begins to fuse, creating carbon and oxygen through the triple alpha process. This reaction requires 3 helium nuclei to combine nearly simultaneously, a process so unlikely that it requires the precise fine-tuning of nuclear physics constants. If the nuclear forces were slightly different, carbon would not form efficiently, and the universe would lack this essential element for organic chemistry and life. For stars massive enough to continue the fusion process beyond helium burning, the nuclear assembly line continues with increasing complexity. Carbon fuses to create neon, magnesium, and sodium. Neon burning produces oxygen and magnesium. Oxygen burning creates silicon, sulfur, and other elements in the middle of the periodic table. Finally, silicon burning produces iron, cobalt, and nickel. the peak of nuclear binding energy, where fusion can no longer release energy. The creation of elements heavier than iron requires a different process entirely, as fusing iron nuclei would absorb energy rather than release it. These heavier elements are created through neutron capture processes that occur under extremely high neutron densities. The rapid neutron capture process, or R process, occurs during supernova explosions and neutron star mergers, where neutron densities are so high that atomic nuclei can capture neutrons faster than they can undergo radioactive decay. When massive stars exhaust their nuclear fuel, they face a catastrophic collapse. The iron core, unable to generate energy through fusion, cannot support the enormous gravitational pressure from the star's outer layers. In less than a second, the core collapses from the size of Earth to approximately 20 kilometers in diameter, creating conditions so extreme that protons and electrons are crushed together to form neutrons. This collapse rebounds in a spectacular supernova explosion that can outshine an entire galaxy. The supernova explosion serves as the universe's ultimate recycling system, dispersing the elements created during the star's lifetime throughout the surrounding interstellar medium. The shock waves from the explosion heat the stellar material to billions of degrees and accelerate it to speeds of thousands of kilometers per second. This enriched material mixes with the existing interstellar gas, increasing its heavy element content and providing the raw materials for the next generation of star and planet formation. The process of stellar nucleosynthesis and supernova enrichment has been ongoing for over 13 billion years, gradually increasing the heavy element content of the universe. Early generations of stars contained almost no heavy elements, while later generations, like our Sun, contain approximately 2% heavy elements by mass. This steady enrichment has been essential for the formation of rocky planets like Earth and the development of complex chemistry necessary for life. The specific elements in your body tell the story of multiple stellar generations and various nucleosynthetic processes. The oxygen you breathe was created primarily in massive stars through helium and carbon burning. The calcium in your bones formed through silicon burning in stars at least 8 times more massive than the Sun. The iron in your hemoglobin, essential for carrying oxygen through your bloodstream, was forged in the cores of massive stars just before they exploded as supernovae. Some elements in your body required even more exotic formation mechanisms. The gold in any jewelry you might wear was likely created during the collision of 2 neutron stars, an event so violent it produces gravitational waves detectable across the universe. These neutron star mergers, recently observed by gravitational wave detectors, are now recognized as major sources of heavy elements like gold, platinum, and uranium through rapid neutron capture processes. The carbon that forms the backbone of all organic molecules has a particularly interesting origin story. Most carbon is produced through helium burning in intermediate mass stars, which later shed their outer layers as planetary nebulae, enriching the interstellar medium. However, the precise nuclear physics that allows carbon formation depends on what's called the Hoyle resonance, a specific energy level in the carbon nucleus that was predicted by astronomer Fred Hoyle specifically to explain carbon's abundance in the universe. The distribution of elements in your body roughly reflects their cosmic abundances and formation processes. Hydrogen, the most abundant element in the universe, makes up about 60% of your body's atoms. Oxygen, created abundantly in massive stars, comprises about 26%. Carbon accounts for about 11%, while nitrogen, also created in stellar interiors through the carbon-nitrogen-oxygen cycle, makes up about 1%. The remaining elements, from calcium and phosphorus to trace metals like zinc and copper, each tell their own story of stellar nucleosynthesis. The timescales involved in creating the elements that make up your body span the entire history of the universe. The hydrogen atoms in your body formed in the first few minutes after the Big Bang. The heavier elements were created over billions of years through multiple generations of stellar evolution. The specific atoms now part of your body may have been incorporated into previous generations of stars and planets before eventually finding their way into the molecular cloud that gave birth to our solar system 4.5 billion years ago. This cosmic connection extends beyond just the elements themselves to the energy that powers life on Earth. The sunlight that drives photosynthesis and ultimately all terrestrial ecosystems comes from nuclear fusion reactions in the sun's core. The same basic process that created the heavy elements in ancient stars. In a sense, we are not only made of star stuff, but also powered by stellar nuclear reactions, creating an intimate connection between biological processes and cosmic physics. The realization that we are made of star stuff has profound implications for our understanding of life's place in the universe. The same physical processes that create elements in stellar cores operate throughout the cosmos, suggesting that the raw materials for life should be widely distributed among star-forming regions. The universality of stellar nucleosynthesis implies that rocky planets with complex chemistry should be common outcomes of cosmic evolution, wherever conditions allow star formation to proceed over billions of years. Modern astronomical observations confirm the ongoing process of stellar element creation and dispersal. Space telescopes observe supernova explosions in distant galaxies, while spectroscopic analysis reveals the changing chemical composition of stars and interstellar gas over cosmic time. These observations directly trace the chemical evolution of the universe and confirm our understanding of how elements are created and distributed through stellar processes. The study of stellar nucleosynthesis continues to evolve with new discoveries about stellar evolution and nuclear physics. Recent observations of neutron star mergers have confirmed their role in creating the heaviest elements, while improved stellar evolution models provide increasingly detailed predictions for element production in different types of stars. Laboratory experiments with exotic nuclei help refine our understanding of the nuclear reactions that occur under extreme stellar conditions. The personal connection between your body's atoms and the stars creates a sense of cosmic citizenship that transcends the boundaries of species, planet, and even solar system. Every breath you take contains atoms that were once part of other stars, other worlds, and perhaps even other living beings. The calcium in your teeth may have been forged in a supernova explosion billions of years ago, while the iron in your blood connects you directly to the nuclear physics of stellar cores that burned out long before Earth existed. Fact 12. The coldest temperatures exist in Earth laboratories, not space. Counterintuitively, the coldest temperatures ever achieved in the universe don't exist in the frigid depths of interstellar space, but rather in carefully controlled laboratory environments here on Earth. While the cosmic microwave background radiation gives space an average temperature of about 2.7 Kelvin, just 2.7 degrees above absolute zero. Scientists have created temperatures billions of times colder in laboratory settings, reaching within billionths of a degree of absolute zero, the theoretical limit where all molecular motion would cease. Absolute zero, defined as 0 Kelvin or minus 273.15 degrees Celsius, represents the theoretical temperature at which all thermal motion of particles would stop. At this temperature, atoms would possess only their zero-point quantum mechanical motion, the minimum motion allowed by Heisenberg's uncertainty principle. While absolute zero can never be reached due to quantum mechanical constraints, scientists have developed ingenious methods to approach it more closely than nature achieves anywhere else in the known universe. The quest to reach ultra-low temperatures began in the 19th century with the liquefaction of gases like nitrogen and helium. Each breakthrough in cooling technology opened new frontiers in physics, revealing quantum mechanical behaviors that remain hidden at higher temperatures. The development of helium refrigeration systems allowed scientists to reach temperatures below 4 Kelvin, while the discovery of superfluidity in liquid helium revealed the strange quantum behaviors that emerge when matter is cooled to extreme temperatures. Laser cooling represents one of the most elegant approaches to achieving ultra-low temperatures. This technique uses the momentum transfer from photons to slow down atoms, effectively cooling them. When atoms absorb and emit photons in a carefully controlled laser field, the net effect removes kinetic energy from their motion. The Doppler effect ensures that moving atoms preferentially absorb photons that oppose their motion, creating a velocity-dependent friction that slows atoms down to speeds of centimeters per second, rather than the hundreds of meters per second typical at room temperature. The laser cooling process begins with trapping atoms using intersecting laser beams tuned slightly below an atomic transition frequency. Due to the Doppler effect, Atoms moving toward a laser beam see the light shifted to higher frequency, bringing it into resonance with the atomic transition. These atoms absorb photons and experience a force opposing their motion. Atoms moving away from the laser see the light shifted to lower frequency, making absorption less likely. This creates a velocity-dependent force that always opposes atomic motion, regardless of direction. Magnetic trapping provides another essential tool for achieving ultra-low temperatures. Atoms with magnetic moments can be trapped in carefully designed magnetic field configurations that create potential wells in space. These magnetic traps allow scientists to isolate small numbers of atoms from their thermal environment while subjecting them to additional cooling techniques. The combination of laser cooling and magnetic trapping has enabled temperatures as low as a few nanokelvin, billionths of a degree above absolute zero. Evaporative cooling, borrowed from nature's own cooling mechanisms, allows scientists to reach even lower temperatures. Just as perspiration cools your skin by removing the highest energy molecules, evaporative cooling removes the most energetic atoms from a trapped sample, leaving behind increasingly cold populations. This process continues until the remaining atoms form quantum degenerate gases, states of matter where quantum mechanics dominates over classical physics. The achievement of Bose-Einstein condensation in dilute atomic gases represents one of the most remarkable accomplishments in low-temperature physics. At temperatures below a few hundred nanokelvin, bosonic atoms begin to occupy the same quantum state, forming a macroscopic quantum object where thousands or millions of atoms behave as a single quantum entity. This state of matter, predicted by Einstein in 1925, exhibits properties like superfluidity and coherence that make it behave more like a laser beam than ordinary matter. Fermionic atoms, which obey different quantum statistics than bosons, create their own exotic quantum states at ultra-low temperatures. These fermionic quantum gases can simulate the behavior of electrons in metals and superconductors, providing insights into fundamental condensed matter physics. Scientists have created fermionic superfluids and studied quantum phase transitions that illuminate the quantum nature of matter under extreme conditions. The experimental techniques for achieving ultra-low temperatures require extraordinary precision and isolation from thermal disturbances. Ultra-high vacuum systems remove residual gas molecules that could heat the sample, while multiple layers of magnetic shielding protect against magnetic field fluctuations. Vibration isolation systems prevent mechanical disturbances from affecting the delicate quantum states, while sophisticated laser systems provide the precise frequency control needed for laser cooling and trapping. The applications of ultra-low temperature physics extend far beyond fundamental research into practical technologies that may revolutionize computing, sensing, and timekeeping. Quantum computers operating at ultra-low temperatures can maintain quantum coherence for extended periods, enabling complex quantum calculations. Atomic clocks based on laser-cooled atoms achieve precisions better than 1 part in 10 to the 18th power, allowing tests of fundamental physics and improvements to GPS and other timing-dependent technologies. The study of ultra-low temperature matter has revealed new states that don't exist at higher temperatures or anywhere else in nature. Spin glasses, quantum Hall fluids, and topological insulators represent just a few examples of exotic quantum matter that emerges when thermal fluctuations are suppressed. These states often exhibit properties that could enable revolutionary technologies, from dissipationless electronics to fault-tolerant quantum computers. Ultra-low temperature physics also provides unique insights into the quantum nature of gravity and space-time. Experiments with Bose-Einstein condensates in carefully designed potentials can simulate the behavior of quantum fields in curved space-time, providing laboratory analogs for studying black hole physics, cosmological expansion, and other gravitational phenomena that remain inaccessible to direct observation. The contrast between laboratory achievements and cosmic temperatures highlights the remarkable ingenuity of human scientific endeavor. While the universe naturally provides extreme environments with enormous energies, pressures, and magnetic fields, achieving extreme cold requires sophisticated technology and precise control that surpass nature's own cooling mechanisms. Interstellar space, despite its reputation for cold, maintains a temperature set by the cosmic microwave background radiation left over from the Big Bang. Recent advances in cooling technology continue to push toward even lower temperatures and larger sample sizes. Techniques like sympathetic cooling, where one species of atoms cools another through controlled interactions, and optical cooling methods that directly remove entropy from atomic samples promise to achieve temperatures in the picokelvin range, trillionths of a degree above absolute zero. These ultra-low temperatures may reveal new quantum phenomena and enable applications that remain unimaginable today. The philosophical implications of achieving temperatures colder than space challenge our understanding of heat, energy, and the relationship between laboratory science and natural phenomena. The ability to create conditions more extreme than those found naturally in the universe demonstrates the power of scientific methodology and human creativity to transcend the limitations of our terrestrial environment. Future developments in ultra-low temperature physics may lead to practical applications that seem like science fiction today. Room temperature superconductors, perfect thermal insulators, and quantum devices that maintain coherence indefinitely could emerge from our growing understanding of matter's behavior at the quantum mechanical limit. The coldest temperatures in the universe, created not in the depths of space, but in the controlled environments of terrestrial laboratories, continue to reveal new aspects of reality that push the boundaries of human knowledge and technological capability. The achievement of ultra-low temperatures represents one of humanity's most precise technological accomplishments, requiring control over matter and energy at levels that approach fundamental quantum limits. These temperatures, colder than anything found in the natural universe, provide windows into quantum reality that remain closed at all other accessible temperatures, revealing the strange and beautiful world of quantum mechanics that underlies all of physical reality. Fact 13. Sound cannot travel through the vacuum of space. One of the most fundamental differences between Earth and space involves the propagation of sound. While science fiction movies often depict space battles with roaring engines and explosive sound effects, the reality is that space is completely silent. Sound cannot travel through the vacuum of space because sound waves require a medium, such as air, water, or solid materials, to propagate, and space is essentially empty, lacking the matter necessary to carry acoustic vibrations from one location to another. Sound waves are mechanical vibrations that travel through matter by causing molecules to oscillate back and forth. When you speak, your vocal cords create pressure waves in the air around them. These waves consist of alternating regions of compressed and rarefied air molecules that propagate outward at approximately 343 meters per second under standard atmospheric conditions. The vibrating air molecules transfer energy to neighboring molecules, creating a chain reaction that carries the sound wave from its source to your ears. The mechanism of sound transmission requires physical contact between molecules. In air, sound waves propagate as longitudinal waves, where air molecules oscillate parallel to the direction of wave propagation. Areas of compression, where molecules are pushed together, alternate with areas of rarefaction, where molecules are pulled apart. This molecular dance carries acoustic energy through the medium, allowing us to hear everything from whispered conversations to thunderous explosions. Different materials transmit sound at different speeds and with varying efficiency. Sound travels faster through denser materials because the closer molecular spacing allows more efficient energy transfer. In water, sound travels at approximately 1,500 meters per second, over 4 times faster than in air. In steel, sound can travel at speeds exceeding 6,000 meters per second. The speed and quality of sound transmission depend on the material's density, elasticity, and temperature. Space, however, presents a fundamentally different environment. The vacuum of space contains an average of fewer than 1 atom per cubic centimeter in interstellar regions, compared to approximately 25 quintillion molecules per cubic centimeter in Earth's atmosphere at sea level. This incredibly low density means that atoms and molecules are separated by vast distances on molecular scales, making it impossible for mechanical vibrations to propagate as they do in terrestrial environments. The silence of space has profound implications for how events unfold in the cosmic environment. Massive explosions that would create deafening sounds on Earth, such as the collision of neutron stars or the explosion of supernovae, occur in complete silence from the perspective of mechanical sound waves. The enormous energies involved in these cosmic events are transmitted through electromagnetic radiation and gravitational waves rather than acoustic vibrations. This doesn't mean that space is entirely devoid of wave phenomena. Electromagnetic waves, including light, radio waves, X-rays, and gamma rays, can propagate through empty space because they don't require a material medium. These waves consist of oscillating electric and magnetic fields that can travel through vacuum at the speed of light. Similarly, gravitational waves, ripples in the fabric of space-time itself, can propagate through empty space, carrying information about accelerating massive objects across cosmic distances. The interstellar medium, while incredibly sparse by terrestrial standards, does contain enough matter to support very low-frequency acoustic waves under certain conditions. These waves, with frequencies far below human hearing, can propagate through the tenuous gas that fills the space between stars. However, these interstellar sound waves travel extremely slowly and carry very little energy compared to electromagnetic radiation, making them irrelevant for most practical purposes and completely inaudible to any conceivable biological hearing system. The absence of sound in space creates unique challenges for human space exploration. Astronauts cannot hear sounds from outside their spacecraft or spacesuits, making direct acoustic communication impossible in the vacuum environment. All communication between astronauts during spacewalks must occur through radio systems that convert sound waves to electromagnetic signals inside one spacesuit, transmit them through space as radio waves, and convert them back to sound waves inside another spacesuit. This acoustic isolation also affects how astronauts perceive and respond to events around them. Mechanical problems with spacecraft equipment, impacts from micrometeorites, or other potentially dangerous events that would create warning sounds in terrestrial environments occur silently in space. Astronauts must rely on visual indicators, tactile feedback, and electronic monitoring systems to detect problems that might otherwise announce themselves through sound. The physics of sound propagation in space environments becomes more complex when considering spacecraft interiors and planetary atmospheres. Inside pressurized spacecraft, sound behaves much as it does on Earth, though the confined space and different atmospheric compositions can affect acoustic properties. On planets with atmospheres, such as Mars or Venus, sound can propagate, but the different atmospheric densities, compositions, and pressures create acoustic environments very different from Earth's. Mars, with its thin atmosphere composed primarily of carbon dioxide, would dramatically alter how sounds are perceived. The lower atmospheric pressure would make sounds much quieter, while the different molecular composition would affect the speed of sound propagation and the frequency response of the acoustic environment. Recordings from Mars rovers have captured the sounds of wind and mechanical operations, but these sounds would be barely audible and strangely altered compared to their terrestrial counterparts. The study of acoustic properties in extreme environments has practical applications for space exploration and technology development. Understanding how sound behaves in different atmospheric conditions helps engineers design communication systems, life support equipment, and scientific instruments for various planetary environments. The absence of sound transmission through vacuum also influences spacecraft design, where mechanical vibrations must be controlled through solid connections rather than acoustic damping. The silence of space has philosophical and psychological implications for human space exploration. The profound quiet of the vacuum environment creates a sensory experience unlike anything available on Earth. Astronauts often describe the eerie silence of spacewalks, where the only sounds are their own breathing and the mechanical noises transmitted through their spacesuit's solid components. This silence can be both peaceful and unsettling, contributing to the unique psychological challenges of space exploration. The contrast between space's silence and Earth's acoustic richness highlights the importance of atmospheric environments for biological systems. Sound plays crucial roles in animal communication, navigation, and survival strategies. The evolution of hearing in terrestrial organisms reflects the constant presence of mechanical wave transmission through atmospheric and aquatic environments. In the silence of space, life as we know it would need to rely entirely on other forms of communication and environmental sensing. Modern space exploration continues to reveal new aspects of how acoustic phenomena behave in extreme environments. The detection of sounds from space by radio telescopes actually involves the conversion of electromagnetic radiation into audible frequencies, allowing scientists to hear radio emissions from planets, stars, and galaxies. These converted signals provide intuitive ways to analyze complex electromagnetic phenomena, but shouldn't be confused with actual acoustic transmission through space. The future of human space exploration will require continued adaptation to the silent environment of space. Advanced spacecraft designs must account for the lack of acoustic warning systems, while psychological support systems must help astronauts adapt to the profound silence of the vacuum environment. As humanity ventures farther into the cosmos, the silence of space will remain a constant reminder of how different the cosmic environment is from our terrestrial home, where sound waves carry information, beauty, and connection across the acoustic landscape of our planet's atmosphere. Fact 14. Black holes don't actually suck things in like vacuums. Despite popular portrayals in science fiction and common misconceptions, black holes don't function like cosmic vacuum cleaners that suck material into their depths. This widespread misunderstanding stems from the dramatic language often used to describe these exotic objects and the natural human tendency to visualize them as holes in space. In reality, black holes are regions of extremely warped space-time where gravity is so strong that nothing, not even light, can escape once it crosses a critical boundary called the event horizon. The confusion about black holes sucking material arises from misunderstanding the nature of gravitational attraction. Black holes don't possess any special attractive power beyond what their mass would normally provide. If our sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting at exactly the same distance and speed as it does now. The planets wouldn't spiral inward toward the black hole any more than they currently spiral toward the sun. The gravitational force depends only on mass and distance, not on whether that mass is concentrated in a normal star or compressed into a black hole. The key to understanding black holes lies in recognizing that gravity, according to Einstein's general relativity, is not a force in the traditional sense, but rather a curvature of space-time itself. Massive objects warp the fabric of space-time, creating what we experience as gravitational attraction. Black holes represent the extreme case where this warping becomes so severe that space-time curves back on itself, creating a region from which nothing can escape once it enters. The event horizon marks the boundary where the escape velocity equals the speed of light. Outside the event horizon, objects can still escape the black hole's gravitational influence if they have sufficient velocity. Spacecraft could orbit a black hole safely at appropriate distances, just as planets orbit stars. The danger comes not from being sucked in, but from venturing too close to the event horizon, or from the tidal forces that stretch objects approaching the black hole. Tidal forces represent the real mechanism by which black holes capture and destroy material. These forces arise from the difference in gravitational strength across the extent of an object. The side of an object closer to the black hole experiences stronger gravitational pull than the far side, creating a stretching effect. For stellar mass black holes, these tidal forces become extreme, very close to the event horizon, potentially tearing apart any object that approaches too closely. A process colorfully termed spaghettification. The process of material actually falling into a black hole involves complex physics quite different from simple suction. As matter spirals inward, it forms an accretion disk, a swirling disk of superheated gas and dust that can reach temperatures of millions of degrees. The friction within this disk causes the material to lose orbital energy and spiral inward more slowly, not through any suction mechanism, but through the gradual loss of angular momentum through electromagnetic interactions. Accretion disks can extend for millions of kilometers around black holes, with material taking months or years to spiral from the outer edge to the event horizon. During this time, the material reaches incredibly high temperatures and emits intense radiation across the electromagnetic spectrum. Paradoxically, these accretion disks make black holes among the brightest objects in the universe, despite the black holes themselves emitting no light. The formation of jets from black holes provides another example of how these objects don't simply suck in everything around them. Many black holes launch powerful jets of material at nearly the speed of light along their rotation axes. These jets carry material away from the black hole, demonstrating that black holes can actually expel matter rather than inevitably consuming everything nearby. The mechanism for jet formation involves the interaction between the black hole's rotation, its magnetic field, and the surrounding accretion disk. The misconception about suction also fails to account for the angular momentum of infalling material. Objects approaching a black hole typically have some sideways motion relative to the black hole's center. This angular momentum must be conserved, causing the objects to orbit the black hole rather than fall straight in. Only through the gradual loss of energy and angular momentum can material eventually cross the event horizon. The behavior of light around black holes illustrates the difference between gravitational attraction and suction. Light rays passing near a black hole follow curved paths through the warped space-time, but they don't get sucked in unless they pass within a critical radius called the photon sphere. At this distance, light can orbit the black hole indefinitely. Outside the photon sphere, light rays can pass by the black hole and continue into space, though their paths will be deflected by the gravitational field. The time dilation effects near black holes create another phenomenon that contradicts the simple suction model. As material approaches the event horizon, time dilation causes processes to appear to slow down from the perspective of distant observers. An observer watching material fall into a black hole would see it appear to slow down and freeze at the event horizon, its light gradually redshifting until it fades from view. This gravitational time dilation effect has nothing to do with suction forces. The detection of black holes relies on observing their gravitational effects on nearby material and their influence on spacetime, rather than any suction phenomena. Astronomers identify black holes by watching stars orbit around invisible massive objects, by detecting the X-ray emission from superheated accretion disks, or by measuring the gravitational waves produced when black holes merge. These observational techniques confirm that black holes behave according to the predictions of general relativity rather than as cosmic vacuum cleaners. The recent direct imaging of black holes by the Event Horizon Telescope has provided visual confirmation of how material behaves around these objects. The images of the supermassive black holes in galaxies M87 and our own Milky Way show bright accretion disks surrounding dark central regions, with material orbiting in accordance with general relativistic predictions rather than being drawn straight inward by suction forces. Hawking radiation represents perhaps the most counterintuitive aspect of black hole physics, showing that black holes actually evaporate over time rather than indefinitely consuming material. According to quantum field theory, virtual particle pairs near the event horizon can become separated, with one particle falling into the black hole, while the other escapes as radiation. This process causes black holes to slowly lose mass and eventually evaporate completely, the opposite of endless consumption. The study of black holes continues to reveal new complexities that further distance these objects from simple suction analogies. Recent theoretical work suggests that black holes might have internal structure, and that information falling into them might be preserved in ways that don't violate quantum mechanics. These developments paint an increasingly sophisticated picture of black holes as complex gravitational phenomena, rather than simple cosmic drains. Understanding the true nature of black holes has practical implications for space exploration and astrophysics. Spacecraft navigating near black holes would need to account for gravitational effects and orbital mechanics rather than worrying about being sucked in from large distances. The energy released by material falling into black holes powers some of the most luminous objects in the universe, providing insights into galaxy formation and evolution. The misconception about black holes sucking material also reflects broader misunderstandings about the nature of gravity and spacetime. Einstein's general relativity revealed gravity to be a geometric phenomenon rather than a force, fundamentally changing how we understand the interaction between matter and spacetime. Black holes represent the most extreme manifestation of this geometric interpretation of gravity, where space-time curvature becomes so pronounced that it creates the ultimate gravitational trap. As our understanding of black holes continues to evolve through theoretical advances and observational discoveries, the simple suction model becomes increasingly inadequate to describe these fascinating objects. Black holes emerge as complex dynamic systems that can both consume and expel material, warp spacetime in extraordinary ways, and provide natural laboratories for testing the most fundamental principles of physics. Far from being cosmic vacuum cleaners, black holes represent some of the most sophisticated and extreme phenomena in the universe, governed by the elegant mathematics of general relativity and quantum mechanics. Fact 15. The universe's expansion is accelerating due to dark energy. One of the most shocking discoveries in modern cosmology came in 1998, when two independent teams of astronomers studying distant supernovae made an observation that fundamentally changed our understanding of the universe's fate. Instead of slowing down as expected from the gravitational pull of all the matter in the universe, the expansion of space itself is actually accelerating. This discovery revealed the existence of a mysterious component called dark energy, which now appears to comprise approximately 68% of the universe's total energy content, and is driving the cosmos toward an increasingly rapid expansion. The discovery emerged from careful observations of Type Ia supernovae, which serve as standard candles for measuring cosmic distances. These stellar explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and explode with remarkably consistent peak brightness. By comparing the observed brightness of these supernovae with their known intrinsic luminosity, astronomers can calculate their distances with high precision. When combined with measurements of how fast these distant galaxies are receding from us, these observations map the expansion history of the universe. The expected scenario, based on our understanding of gravity and matter in the universe, was that cosmic expansion should be slowing down over time. All the matter in the universe, ordinary matter, dark matter, and radiation, creates gravitational attraction that should act as a cosmic brake, gradually reducing the expansion rate. Different amounts of matter would lead to different outcomes. Insufficient matter would result in eternal expansion that slows but never stops, while too much matter would eventually halt expansion and reverse it into a cosmic collapse. What the supernova surveys actually found defied all expectations. Distant supernovae appeared dimmer than predicted, indicating they were farther away than anticipated in a decelerating universe. This could only mean that the expansion rate was smaller in the past and has been increasing over time. The universe's expansion is accelerating. The implications were so startling that both research teams initially suspected systematic errors in their observations, spending months checking and rechecking their data before accepting the revolutionary conclusion. The acceleration of cosmic expansion requires a form of energy that acts opposite to gravity. Instead of pulling things together, it pushes space apart. This mysterious component, dubbed dark energy, must have negative pressure and remain at constant density even as space expands. Unlike matter or radiation, which become less dense as the universe grows larger, dark energy maintains constant energy density, meaning that its total energy content increases as the volume of space increases. The simplest explanation for dark energy is Einstein's cosmological constant, a term he originally introduced into his equations of general relativity to allow for a static universe. Einstein later called this his greatest mistake when Hubble's observations revealed that the universe was expanding. However, the cosmological constant naturally provides the properties needed for dark energy. It creates a repulsive gravitational effect and maintains constant energy density throughout space and time. If dark energy behaves like a cosmological constant, it represents an intrinsic property of empty space itself, a kind of energy built into the vacuum of space-time. This vacuum energy would be completely uniform throughout the universe and unchanging over time. Quantum field theory predicts that empty space should indeed possess energy due to quantum fluctuations, but theoretical calculations yield a vacuum energy density that is approximately 10 to the 120th power larger than what we observe, creating one of the most significant discrepancies between theory and observation in all of physics. Alternative explanations for dark energy involve dynamic fields that change over time and space, similar to the inflaton field, thought to have driven cosmic inflation in the early universe. These quintessence models propose that dark energy arises from a scalar field that slowly evolves, potentially changing its properties over cosmic time. Some quintessence models predict that dark energy could strengthen, weaken, or even change sign in the future, leading to dramatically different fates for the universe. The discovery of accelerating expansion has profound implications for the ultimate fate of the cosmos. In a dark, energy-dominated universe, expansion will continue indefinitely and at an ever-increasing rate. This leads to a scenario called the heat death of the universe, where all matter becomes increasingly diluted and isolated. Stars will eventually exhaust their nuclear fuel. black holes will slowly evaporate through Hawking radiation, and the universe will approach a state of maximum entropy where no further work can be performed. More extreme scenarios arise if dark energy continues to strengthen over time. In a Big Rip scenario, the acceleration becomes so strong that it overcomes all other forces in the universe. First, galaxy clusters would be torn apart as dark energy overcomes their gravitational binding. Then individual galaxies would disperse, followed by solar systems, planets, and eventually atoms themselves, as the fundamental forces become unable to hold matter together against the accelerating expansion of space. The timeline for cosmic evolution in an accelerating universe spans incomprehensibly vast periods. Over the next few billion years, the acceleration will cause distant galaxy clusters to disappear beyond our observable horizon as their recession velocities exceed the speed of light. In about 100 billion years, only our local group of galaxies will remain visible to observers in the Milky Way, creating a much lonelier and apparently smaller universe for future astronomers to study. The measurement of cosmic acceleration has become increasingly precise through multiple independent methods. Large-scale galaxy surveys map the three-dimensional distribution of matter across billions of light years, revealing how the growth of cosmic structure has been affected by dark energy. Observations of the cosmic microwave background provide information about the geometry and content of the universe that constrains dark energy properties. Gravitational lensing studies show how dark energy affects the growth of massive structures over cosmic time. Recent observations have begun to probe whether dark energy has remained constant over cosmic history or has evolved over time. The Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and space-based missions like Euclid are mapping the universe's expansion history with unprecedented precision. These observations will help determine whether dark energy behaves like Einstein's cosmological constant or follows more complex dynamics that could change the universe's ultimate fate. The existence of dark energy raises fundamental questions about the nature of space, time, and energy itself. If dark energy represents the energy of empty space, it suggests that the vacuum possesses physical properties that we don't fully understand. Alternative theories propose that dark energy might not exist at all, and that the observed acceleration could result from modifications to Einstein's general relativity on cosmic scales, or from our universe existing within a higher dimensional space. The coincidence that dark energy began dominating the universe's expansion around the same time that complex structures like galaxies and stars formed has led to speculation about anthropic explanations. Some theories suggest that the observed value of dark energy might be necessary for the formation of structures capable of supporting life, with other possible universes having different dark energy values that prevent the formation of stars and planets. The study of dark energy represents one of the most active frontiers in modern cosmology and fundamental physics. New theoretical frameworks attempt to understand how dark energy fits into a unified description of all fundamental forces. Experimental searches for dark energy particles or fields continue both in terrestrial laboratories and through astronomical observations. The detection of gravitational waves has opened new possibilities for studying dark energy through its effects on the propagation of space-time ripples across cosmic distances. The accelerating expansion driven by dark energy affects not only the future of the universe, but also our current observations of cosmic phenomena. The acceleration influences the distances to astronomical objects, the ages of stars and galaxies, and the formation and evolution of large-scale structures. Understanding dark energy is essential for interpreting observations across all areas of astronomy and cosmology. As we continue to study dark energy through increasingly sophisticated observations and theoretical models, this mysterious component of the universe may reveal new physics beyond our current understanding. The force that is pushing the universe toward an ever faster expansion remains one of the deepest mysteries in science, challenging our most fundamental concepts about the nature of reality and our cosmic future. The discovery that the universe's expansion is accelerating has transformed cosmology from a field focused on understanding the past to one grappling with the profound implications of our accelerating journey into an increasingly empty and isolated cosmic future. Fact 16. Magnetars have magnetic fields that could kill from 1,000 miles away. Among the most extreme objects in the universe, Magnetars represent neutron stars with magnetic fields so powerful they defy comprehension. These cosmic monsters possess magnetic field strengths reaching 10 to the 15th Gauss, approximately 1 quadrillion times stronger than Earth's magnetic field and 1 trillion times stronger than the strongest magnetic fields humans have ever created in laboratories. To put this in perspective, a magnetar's magnetic field is so intense that it could kill a human being from a distance of 1,000 miles away, not through radiation or gravitational effects, but through the direct biological impact of the magnetic field itself. The formation of magnetars begins with the collapse of extremely massive stars, similar to other neutron stars, but with additional factors that amplify their magnetic properties to extraordinary levels. When a star with an initial mass of at least 25 to 30 times that of our Sun exhausts its nuclear fuel, its core collapses catastrophically in less than a second. The collapse concentrates not only the star's mass, but also its magnetic field into a sphere approximately 20 kilometers in diameter, increasing the field strength by a factor of approximately 1 trillion through magnetic flux conservation. The physics governing such extreme magnetic fields pushes the boundaries of our understanding of electromagnetism and quantum mechanics. In magneto-magnetic fields, the quantum mechanical energy levels of atoms become dramatically altered. The cyclotron energy, the energy associated with charged particles spiraling in magnetic fields, exceeds the binding energy of atoms, fundamentally changing the properties of matter. Atoms become elongated into needle-like shapes, with electron orbitals stretched into thin cylinders aligned with the magnetic field direction. The magnetic field strength of magnetars exceeds what physicists call the critical magnetic field, approximately 4.4 times 10 to the 13th Gauss, above which quantum electrodynamic effects become significant. At these field strengths, the vacuum itself becomes birefringent. It affects the polarization of light passing through it. Virtual electron-positron pairs in the quantum vacuum become aligned with the magnetic field, creating an anisotropic medium that affects electromagnetic radiation propagation. The biological effects of such extreme magnetic fields would be immediately lethal to any living organism. Human bodies contain water molecules with hydrogen nuclei that have magnetic moments. In a magnetar's field, these nuclear magnetic moments would experience forces strong enough to disrupt cellular structure at the molecular level. The magnetic field would induce enormous electric fields in conducting biological tissues, creating currents that would instantly destroy nervous system function and cellular integrity. Even more dramatically, the magnetic forces would be strong enough to affect the diamagnetic properties of biological molecules. All matter exhibits some degree of diamagnetism, the tendency to be slightly repelled by magnetic fields. While this effect is normally negligible, in magnetostrength fields it becomes powerful enough to levitate and distort biological tissues. The human body, being largely composed of water and organic molecules, would experience magnetic forces comparable to gravitational forces, leading to potentially fatal deformation and internal disruption. The magnetic field energy of a typical magnetar exceeds the binding energy that holds the neutron star together gravitationally. This creates enormous stresses within the neutron star crust, leading to sudden rearrangements called starquakes. When the rigid neutron star crust can no longer support the magnetic stresses, it fractures and settles into a new configuration. These starquakes release energy equivalent to hundreds of thousands of years of solar output in just a few seconds, creating some of the most powerful electromagnetic events observed in the universe. Magnetar outbursts can have dramatic effects across the solar system and beyond. In December 2004, a magnetar located 28,000 light-years away in the constellation Sagittarius released a burst of gamma rays so intense that it briefly overwhelmed every gamma ray detector in the solar system and caused measurable changes in Earth's ionosphere. The radiation from this event, designated SGR 1806-20, was so powerful that it would have caused significant atmospheric damage if the magnetar had been located within 50 light-years of Earth. The extreme magnetic fields of magnetars affect every aspect of their physics and observational properties. The magnetic field forces electrons to move only along magnetic field lines, creating highly anisotropic electrical conductivity. This leads to complex current systems within the neutron star and its surrounding magnetosphere. The interaction between these currents and the magnetic field generates the high-energy radiation that allows us to detect magnetars across vast cosmic distances. The surface of a magnetar experiences conditions unlike anywhere else in the universe. The magnetic pressure, the pressure exerted by the magnetic field itself, can exceed the material pressure of the neutron star matter. This creates a complex interplay between magnetic forces and gravitational forces that affects the star's structure and surface composition. The magnetic field can support mountains on the neutron star surface that are held up by magnetic pressure rather than material strength. Magnetar atmospheres, if they can be called atmospheres at all, consist of thin layers of highly magnetized plasma, where atoms are distorted beyond recognition. The strong magnetic field creates quantum mechanical effects that make the plasma behavior completely different from any terrestrial plasma. Photons can split into multiple photons or merge together, while the polarization properties of light are dramatically altered by passage through the magnetized vacuum near the star. The discovery and study of magnetars have required the development of new theoretical frameworks for understanding matter and energy under extreme conditions. The combination of intense magnetic fields, high gravitational fields, and exotic matter states creates a natural laboratory for testing physics theories under conditions impossible to replicate on Earth. Magnetars provide insights into quantum chromodynamics, the behavior of matter at nuclear densities, and the fundamental limits of electromagnetic field strength. The rotation of magnetars adds another layer of complexity to their already extreme physics. Young magnetars can rotate several times per second, but their intense magnetic fields interact with surrounding plasma to create electromagnetic braking that slows their rotation much faster than ordinary neutron stars. This rapid spin-down releases enormous amounts of rotational energy that powers the magnetar's high-energy emissions and contributes to the violent rearrangements of the magnetic field structure. The population of known magnetars remains small, with only about 30 confirmed objects identified in our galaxy and nearby galaxies. This rarity reflects both the extreme conditions required for magnetar formation and the relatively short timescales over which they remain active. Most magnetars are thought to remain highly active for only a few thousand years before their magnetic fields decay and their dramatic outbursts cease, making them among the most transient phenomena in stellar astronomy. The study of magnetars continues to reveal new physics and challenge our understanding of extreme states of matter. Recent observations have detected radio pulsations from some magnetars, blurring the traditional distinction between magnetars and ordinary pulsars. Fast radio bursts, mysterious signals from distant galaxies, might originate from magnetars in other galaxies, suggesting these extreme objects play important roles in cosmic phenomena throughout the universe. Future observations of magnetars will benefit from next-generation high-energy telescopes and improved theoretical models of magnetic field evolution. The detection of gravitational waves from magnetar starquakes could provide new insights into neutron star structure and the behavior of matter under extreme magnetic stresses. Laboratory experiments with ultra-high magnetic fields continue to explore the quantum electrodynamic effects that govern magnetophysics. The existence of magnetars reminds us that the universe contains environments so extreme they challenge the very foundations of our physical understanding. These cosmic monsters, with magnetic fields powerful enough to kill from 1,000 miles away, represent nature's most extreme magnetic phenomena and continue to push the boundaries of theoretical physics and observational astronomy. The study of these extraordinary objects provides unique windows into the fundamental laws of physics under conditions that can never be replicated in terrestrial laboratories, ensuring that magnetars will remain among the most fascinating and important objects in the cosmic zoo. Fact 17. Looking at stars means looking into the past. Every time you gaze up at the night sky, you're literally looking backward through time, observing the universe as it existed years, centuries, millennia, or even millions of years ago. This isn't poetic metaphor, but physical reality. Light from astronomical objects takes time to travel across the vast distances of space, creating a natural time machine that allows us to observe cosmic history. The finite speed of light, approximately 300,000 kilometers per second, means that everything we see in the universe shows us how things appeared in the past, not as they exist in the present moment. The concept begins with our nearest star, the Sun, located approximately 150 million kilometers away from Earth. Sunlight takes about 8 minutes and 20 seconds to travel this distance, which means the sun you see in the sky shows you how the sun appeared 8 minutes ago. If the sun were to suddenly disappear, we wouldn't know about it for over 8 minutes. This delay seems trivial in everyday terms, but it establishes the fundamental principle that governs all astronomical observation. Distance equals time delay. The effect becomes more pronounced as we look at increasingly distant objects. The nearest star to our solar system, Proxima Centauri, lies approximately 4.2 light-years away. When you observe this star, you're seeing light that left its surface over 4 years ago. The star might have changed dramatically, dimmed, or even exploded in a supernova during those 4 years, but we wouldn't know about it until the light from those events reaches Earth. This temporal aspect of starlight creates a profound realization. The stars you see in familiar constellations like the Big Dipper or Orion left their surfaces at different times in the past. Some stars in these constellations are relatively nearby, showing us their appearance from decades ago, while others are hundreds of light years distant, displaying how they looked during the Middle Ages or the time of ancient civilizations. The patterns we perceive as constellations represent a false simultaneity, a collection of stars from different epochs artificially frozen into apparent contemporaneity by the human eye. The temporal nature of astronomical observation becomes even more remarkable when we consider distant galaxies. The Andromeda Galaxy, our nearest large galactic neighbor, appears as it existed approximately 2.5 million years ago. The light we observe tonight left Andromeda when early human ancestors were just beginning to walk upright on the African savanna. Even more distant galaxies show us the universe as it existed billions of years ago, during epochs when Earth was still forming, or when life had not yet emerged on our planet. This light travel time effect has profound implications for our understanding of cosmic evolution and structure. When astronomers observe the most distant galaxies detectable by advanced telescopes like the Hubble Space Telescope or the James Webb Space Telescope, they're seeing these objects as they appeared when the universe was only a small fraction of its current age. These distant galaxies appear smaller, less structured, and often more actively star-forming than nearby galaxies, providing direct observational evidence for cosmic evolution and galaxy formation processes. The cosmic microwave background radiation represents the ultimate example of looking into the past through astronomical observation. This radiation, detected uniformly across the sky, shows us the universe as it appeared approximately 380,000 years after the Big Bang, when the cosmos first became transparent to light. Before this epoch, the universe was so hot and dense that photons couldn't travel freely through space. The cosmic microwave background provides a baby picture of the universe, showing the tiny density fluctuations that would eventually grow into the galaxies and large-scale structures we observe today. The finite speed of light also affects our understanding of simultaneity and causality on cosmic scales. Events that appear to occur simultaneously when observed from Earth actually happened at different times due to light travel delays. This creates challenges for understanding the true temporal relationships between astronomical phenomena and requires careful analysis to determine the actual sequence of cosmic events. Stellar evolution timescales add another layer of complexity to the temporal nature of starlight. Massive stars evolve rapidly, living for only a few million years before exploding as supernovae. When we observe such stars in distant galaxies, we might be seeing them during phases of their evolution that ended long ago. Some stars we observe may have already exploded, with their supernova light still traveling toward Earth. Conversely, stars that we see exploding in distant galaxies actually detonated years or decades ago, depending on their distance from us. The expansion of the universe further complicates the relationship between distance and look-back time. As light travels from distant objects, the universe continues to expand, increasing the distance between the source and observer. This means that objects we observe at great distances are now much farther away than they were when their light began its journey toward us. The most distant galaxies we can observe are now located approximately 46 billion light-years away, even though their light has been traveling for less than 14 billion years. Variable stars provide dramatic examples of how we observe stellar changes from the past. Stars like Cepheid variables pulsate with regular periods, changing their brightness over days or weeks. When we observe these brightness variations in distant galaxies, we're seeing pulsations that occurred years or millennia ago. The timing of these variations helps astronomers measure distances to far galaxies and study stellar physics under conditions that existed in the cosmic past. The study of supernovae illustrates how astronomical light curves reveal information about past events. When a massive star explodes as a supernova, it brightens dramatically over days or weeks, then gradually fades over months or years. Observing supernovae in distant galaxies shows us these spectacular stellar deaths as they unfolded in the past, providing information about stellar evolution, nuclear physics, and cosmic chemical evolution during earlier epochs of universal history. Gravitational lensing adds yet another temporal dimension to astronomical observation. When light from distant objects passes near massive galaxies or galaxy clusters, its path is bent by gravitational effects, often creating multiple images of the same object. These different light paths have different lengths, so the multiple images show the same object at slightly different times in the past. In some cases, astronomers observed the same supernova explosion multiple times as light from the event arrives via different gravitational light paths. The concept of look-back time has practical implications for understanding cosmic phenomena and testing theories of physics. Observations of distant objects allow astronomers to study physical processes under conditions that existed billions of years ago, when the universe was younger, denser, and had different chemical composition. These observations provide crucial tests of theories about cosmic evolution, galaxy formation, and the fundamental constants of physics. Modern technology continues to push the boundaries of how far back in time we can observe. The James Webb Space Telescope is designed to detect infrared light from the very first galaxies that formed after the cosmic dark ages, potentially observing objects as they appeared over 13 billion years ago. These observations will show us the universe during its first billion years, revealing how the earliest structures formed and evolved. The realization that astronomical observation is time travel highlights the unique perspective that astronomy provides on natural history. Unlike other sciences, which must reconstruct past events from present evidence, astronomy allows direct observation of the past through the light that has been traveling toward us across cosmic distances. Each night, amateur and professional astronomers alike become time travelers, peering into the cosmic past through the simple act of looking up at the stars, and realizing that the light entering their eyes began its journey years, decades, centuries, or millennia ago, carrying information about the universe as it once was rather than as it exists today. Fact 18. The Hercules Corona Borealis Great Wall spans 10 billion light years. The largest known structure in the observable universe challenges our fundamental understanding of cosmic evolution and the limits of structure formation. The Hercules Corona Borealis Great Wall stretches across approximately 10 billion light-years of space, roughly 1/4 the diameter of the entire observable universe. This colossal structure consists of a vast network of galaxies, galaxy clusters, and dark matter arranged in a web-like pattern that defies theoretical predictions about how large structures can grow in the time since the Big Bang. The discovery of this enormous structure emerged from mapping the three-dimensional distribution of gamma-ray bursts across the sky. Gamma-ray bursts serve as excellent cosmic distance markers because they can be observed across vast portions of the universe, and their distances can be determined from their redshifts. When astronomers plotted the positions of gamma-ray bursts in space, they noticed an unusual clustering pattern in the direction of the constellations, Hercules and Corona Borealis, leading to the structure's name. The scale of the Hercules Corona Borealis Great Wall is difficult to comprehend. If you could travel at the speed of light, it would take 10 billion years to cross from one end to the other. This means the structure is so large that light from galaxies on one side is still traveling toward galaxies on the other side, having begun its journey when the universe was less than 4 billion years old. The structure contains billions of galaxies and an almost unimaginable amount of mass, equivalent to millions of trillions of stars like our Sun. The existence of such a massive structure poses significant challenges to our understanding of cosmic evolution and structure formation. According to the standard model of cosmology, structures in the universe grow through gravitational collapse over billions of years. Dark matter clumps together first, followed by ordinary matter that falls into the dark matter wells and eventually forms stars and galaxies. However, theoretical calculations suggest that there hasn't been enough time since the Big Bang for structures as large as the Hercules Corona Borealis Great Wall to form through conventional gravitational processes. The cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales, places theoretical limits on the maximum size of cosmic structures. According to this principle, structures larger than approximately 1.2 billion light-years should not exist because they would violate the assumption of cosmic uniformity. The Hercules Corona Borealis Great Wall exceeds this limit by nearly an order of magnitude, suggesting either that our understanding of structure formation is incomplete or that the cosmological principle may not apply on the largest observable scales. The formation of such massive structures requires understanding the complex interplay between dark matter, dark energy, and ordinary matter over cosmic timescales. Computer simulations of cosmic evolution can reproduce the formation of galaxy clusters and smaller structures, but they struggle to explain how something as large as the Hercules Corona Borealis Great Wall could have assembled in the time available since the Big Bang. The structure may represent a relic of quantum fluctuations from the inflationary epoch, stretched to enormous scales by the rapid expansion of space. The internal structure of the Great Wall reveals the complex architecture of the cosmic web. Rather than being a solid wall of matter, it consists of interconnected filaments of dark matter and galaxies surrounding vast empty regions called cosmic voids. These filaments can be hundreds of millions of light-years long and tens of millions of light-years wide, creating a foam-like structure that permeates the largest scales of the universe. The total volume of the structure is mostly empty space, with matter concentrated along the filamentary network. The gravitational influence of the Hercules Corona Borealis Great Wall affects the motion of galaxies across a significant portion of the observable universe. Galaxies within and around the structure show peculiar velocities, motions beyond those expected from the overall expansion of the universe. These peculiar velocities result from the gravitational attraction of the massive structure and provide observational evidence for its existence beyond the statistical clustering of gamma-ray bursts. The discovery of this enormous structure has implications for our understanding of dark energy and the fate of the universe. Dark energy, which drives the accelerated expansion of space, opposes the gravitational collapse that builds cosmic structures. The balance between dark energy's repulsive effect and gravity's attractive force determines how large structures can grow over time. The existence of the Hercules Corona Borealis Great Wall suggests that this balance may be more complex than previously thought, or that dark energy's properties may have evolved over cosmic history. Observations of the structure provide insights into the early universe and the conditions that prevailed during the first few billion years after the Big Bang. The galaxies within the Great Wall formed when the universe was much younger and denser than it is today. Studying these ancient galaxies reveals how star formation, galaxy evolution, and large-scale structure formation proceeded during the universe's youth, providing crucial data for testing theories of cosmic evolution. The Hercules Corona Borealis Great Wall is not unique. Astronomers have discovered several other enormous structures that challenge conventional understanding of cosmic architecture. The Sloan Great Wall, the giant GRB ring, and the huge Large Quasar Group all represent massive cosmic structures that approach or exceed theoretical size limits. The existence of multiple such structures suggests that the universe's large-scale organization may be more complex and varied than predicted by standard cosmological models. The statistical significance of the Great Wall's existence continues to be debated within the astronomical community. Some researchers argue that the clustering pattern could result from random chance rather than representing a genuine physical structure. Others contend that the statistical evidence is compelling and that the structure represents a real cosmic feature that requires explanation within our cosmological framework. Ongoing surveys of gamma-ray bursts and galaxy positions will help resolve this debate. The study of such massive structures requires international collaboration and the most powerful astronomical instruments available. Large-scale surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and future projects like the Large Synoptic Survey Telescope Map, the three-dimensional distribution of galaxies across billions of light years. These surveys reveal the cosmic web's intricate structure and help identify the largest cosmic structures that challenge our understanding of the universe. The existence of the Hercules Corona Borealis Great Wall raises fundamental questions about the nature of space, time, and matter on cosmic scales. If structures this large can exist, what does this tell us about the initial conditions of the universe and the physical processes that operated in its early epochs? The structure may provide evidence for exotic physics beyond the standard model of cosmology, such as modified gravity theories or alternative models of dark matter and dark energy. Future observations will continue to refine our understanding of this colossal structure and its implications for cosmology. Advanced telescopes and surveys will map its detailed structure, measure the properties of its constituent galaxies, and determine how it fits into the broader cosmic web. These observations will help determine whether the Hercules Corona Borealis Great Wall represents an extreme but explicable outcome of standard cosmic evolution, or evidence for new physics that governs the universe's larger scales. The discovery of such enormous cosmic structures reminds us that the universe continues to surprise us with its complexity and scale. The Hercules Corona Borealis Great Wall represents one of the most extreme examples of cosmic architecture, challenging our theoretical frameworks and expanding our appreciation for the intricate organization of matter and energy across the vast expanses of space and time that define our cosmic home. Fact 19. Hypervelocity stars travel fast enough to escape galaxies. In the depths of our galaxy, a small population of rogue stars are traveling at speeds so extreme they can break free from the Milky Way's gravitational embrace entirely. These hypervelocity stars race through space at velocities exceeding 1,000 kilometers per second, fast enough to travel from Earth to the Moon in less than 7 minutes. At such incredible speeds, these stellar refugees will eventually escape our galaxy completely, embarking on lonely journeys through the vast emptiness of intergalactic space, where they will wander for billions of years as cosmic nomads. The discovery of hypervelocity stars came as a surprise to astronomers who had long assumed that stars were permanently bound to their home galaxies by gravitational forces. The first confirmed hypervelocity star, designated Shki 0437-5439, was identified in 2005 as a hot blue star moving away from the galactic center at approximately 700 kilometers per second. This discovery opened an entirely new field of stellar astronomy and revealed previously unknown violent processes occurring at the heart of our galaxy. The formation mechanism for most hypervelocity stars involves interactions with the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. This cosmic monster, with a mass approximately 4 million times that of our Sun, creates an environment of extreme gravitational forces where stellar dynamics become chaotic and unpredictable. When binary star systems venture too close to this central black hole, tidal forces can disrupt the binary, sending one star plunging into the black hole while catapulting its companion outward at tremendous velocity. This stellar slingshot mechanism, first proposed by theoretical astrophysicist Jack Hills in 1988, explains how ordinary stars can achieve the extreme velocities necessary to escape galactic gravity. The process requires precise conditions. A binary star system must approach the supermassive black hole at just the right distance and angle for tidal forces to separate the stars without destroying them entirely. Computer simulations show that this mechanism can accelerate stars to velocities well above the galaxy's escape velocity, which ranges from 500 to 700 kilometers per second depending on location. The journey of a hypervelocity star from the galactic center to the galaxy's edge takes tens of millions of years, during which the star maintains its extreme velocity while moving through the galaxy's gravitational field. Most hypervelocity stars are massive, hot blue stars with lifetimes of only a few tens of millions of years. This creates a race against time. The star must escape the galaxy before it exhausts its nuclear fuel and dies. Some hypervelocity stars will successfully escape and continue burning in intergalactic space, while others will explode as supernovas while still bound to the galaxy. Observations of hypervelocity stars provide unique insights into the structure and mass distribution of our galaxy. As these stars travel outward, they probe the gravitational field at different distances from the galactic center, allowing astronomers to map the distribution of dark matter in the galactic halo. The trajectories of hypervelocity stars act like test particles, revealing the three-dimensional gravitational landscape of the Milky Way with unprecedented detail. The search for hypervelocity stars has revealed a diverse population of high-velocity objects with various origins and properties. While the classical hypervelocity stars originate from interactions with the central black hole, other mechanisms can also accelerate stars to extreme velocities. Supernova explosions in binary systems can sometimes kick the surviving star to high velocities through asymmetric mass ejection. Interactions between star clusters or encounters with intermediate mass black holes can also accelerate individual stars, though typically to lower velocities than the central black hole mechanism. The chemical composition of hypervelocity stars tells the story of their origins in the galactic center, where stellar evolution proceeds under conditions very different from the solar neighborhood. These stars often show enhanced abundances of heavy elements produced by multiple generations of massive stars that have lived and died in the crowded central regions of the galaxy. Some hypervelocity stars also show evidence of having been stripped from other galaxies during past galactic interactions, representing stellar immigrants that have been accelerated during their journey through our galaxy. Advanced surveys using space-based telescopes and ground-based observatories continue to discover new hypervelocity stars throughout the galaxy. The European Space Agency's Gaia mission has revolutionized the field by providing precise measurements of stellar positions and velocities for over 1 billion stars. This unprecedented dataset has revealed hundreds of candidate hypervelocity stars and refined our understanding of the galactic velocity distribution, showing that high-velocity stars are more common than previously thought. The fate of hypervelocity stars that successfully escape the galaxy depends on their mass and evolutionary state. Massive stars will continue burning for tens of millions of years in intergalactic space before exploding as supernovae, enriching the intergalactic medium with heavy elements. Lower mass stars, though rare among the hypervelocity population, could potentially survive for billions of years as intergalactic wanderers. These stellar exiles would experience a lonely existence, surrounded by the vast emptiness of intergalactic space with the nearest star potentially millions of light years away. The study of hypervelocity stars has implications for understanding stellar populations in other galaxies and the intergalactic medium. Every galaxy with a supermassive black hole should produce some hypervelocity stars, contributing to a population of intergalactic stars that exist between galaxies. These intergalactic stars are extremely difficult to detect due to their isolation and the lack of background light for contrast, but they may comprise a significant fraction of the stars in galaxy clusters. Recent theoretical work has explored exotic mechanisms for producing hypervelocity stars, including interactions with primordial black holes, dark matter substructure, or even gravitational wave recoil from black hole mergers. These alternative mechanisms could explain some hypervelocity stars with unusual properties or trajectories that don't match the classical Hills mechanism. The diversity of hypervelocity star properties suggests that multiple acceleration mechanisms may operate in galactic environments. The discovery of hypervelocity stars traveling in unusual directions has provided evidence for the complex dynamical history of the galactic center. Some hypervelocity stars appear to originate from directions other than the current location of Sagittarius A star, suggesting that the central black hole may have migrated over time, or that other massive objects in the galactic center have contributed to stellar acceleration. These observations help reconstruct the dynamical evolution of the galaxy's central regions over millions of years. The extreme velocities of hypervelocity stars create relativistic effects that must be accounted for in precise observations. Although their speeds remain well below the speed of light, the fastest hypervelocity stars experience measurable time dilation and relativistic beaming effects. These subtle corrections become important for accurate trajectory calculations and age determinations, highlighting the intersection between stellar astronomy and special relativity. Future observations will continue to expand our census of hypervelocity stars and refine our understanding of their origins and evolution. Advanced spectroscopic surveys will measure detailed chemical compositions and stellar parameters, while improved astrometric measurements will trace their trajectories back to their points of origin. Space-based telescopes optimized for wide-field surveys may discover hypervelocity stars in other galaxies, providing comparative studies of galactic dynamics and supermassive black hole interactions across the universe. The phenomenon of hypervelocity stars illustrates the violent and dynamic nature of galactic centers, where extreme gravitational forces can overcome the binding energy that normally keeps stars attached to their home galaxies. These stellar speed demons represent some of the fastest moving stars known to science, racing through space at velocities that will carry them beyond the gravitational reach of the Milky Way and into the cosmic void. Their discovery has opened new avenues for studying galactic structure, black hole physics, and stellar dynamics, while reminding us that even in the apparently stable realm of stellar astronomy, extreme events can send stars on incredible journeys across the cosmos at speeds that challenge our intuitive understanding of stellar motion and galactic structure. Fact 20. Mars was once in our Sun's habitable zone. The concept of habitable zones around stars, regions where liquid water can exist on planetary surfaces, reveals a dynamic aspect of planetary systems that changes over billions of years as stars evolve. Our Sun, like all main sequence stars, has been gradually increasing in brightness throughout its 10 billion year lifetime, causing the habitable zone to slowly move outward from its original position. This stellar evolution means that Mars, the red planet we know today as a cold, desert world, was once located within the Sun's habitable zone and may have experienced Earth-like conditions billions of years ago. When our solar system formed approximately 4.6 billion years ago, the young Sun was significantly dimmer than it is today, roughly 25 to 30% less luminous according to stellar evolution model. This phenomenon, known as the faint young Sun paradox, initially puzzled scientists because Earth should have been frozen solid under such dim illumination. Yet geological evidence clearly shows that liquid water existed on Earth's surface throughout most of its history. The resolution to this paradox involves understanding how planetary atmospheres and stellar evolution interact over geological timescales. The early Sun's reduced luminosity placed the habitable zone much closer to the star than its current position. During the first billion years of the solar system's existence, the habitable zone extended from approximately 0.7 to 1.3 astronomical units from the Sun, a range that would have included Mars, which orbits at an average distance of 1.5 astronomical units. This means Mars spent its first billion years or more bathed in solar radiation, suitable for maintaining liquid water on its surface, provided it possessed a sufficiently thick atmosphere. Evidence for Mars's warmer, wetter past comes from multiple sources of geological and atmospheric data collected by robotic missions over the past several decades. Orbital imaging reveals extensive networks of ancient river valleys, lake beds, and floodplains carved into the Martian surface during a period called the Noachian Epoch, which lasted from the planet's formation until approximately 3.7 billion years ago. These features indicate that liquid water once flowed freely across the Martian landscape, creating erosional patterns identical to those formed by rivers and lakes on Earth. The Martian atmosphere during this early epoch was likely much thicker and warmer than today's thin, cold atmosphere. Current atmospheric pressure on Mars is less than 1% of Earth's atmospheric pressure, too low to support liquid water except in the deepest basins and only under specific temperature conditions. However, isotopic analysis of the current atmosphere suggests that Mars has lost most of its original atmosphere over billions of years, with the early atmosphere potentially being dense enough to support a greenhouse effect that could maintain liquid water even at Mars's greater distance from the Sun. The loss of Mars's thick atmosphere occurred through several mechanisms related to the planet's smaller size and lack of a global magnetic field. Mars has approximately 11% of Earth's mass and 38% of Earth's gravity, making it less capable of retaining atmospheric gases over geological timescales. Additionally, Mars lacks the strong global magnetic field that helps protect Earth's atmosphere from solar wind erosion. Without this magnetic shield, charged particles from the solar wind gradually stripped away the Martian atmosphere, transforming the planet from a potentially habitable world into the cold, dry desert we observe today. The timing of Mars's transition from a potentially habitable world to its current state coincides with major changes in solar system dynamics and stellar evolution. As the Sun gradually brightened over its first few billion years, the habitable zone migrated outward, eventually leaving Mars behind while encompassing Earth more completely. Simultaneously, the loss of Mars's atmosphere accelerated due to impact events from the late heavy bombardment period and continued solar wind erosion, creating a feedback loop that accelerated the planet's transformation. Mineralogical evidence from Mars missions provides additional support for the planet's warmer past. The Mars rovers and orbiters have identified clay minerals, sulfates, and other hydrated compounds that form only in the presence of liquid water. Some of these minerals require specific pH conditions and temperatures that suggest Mars once had stable bodies of water with chemical compositions suitable for supporting microbial life. The discovery of seasonal methane emissions and organic compounds in Martian rocks further suggests that the planet may have once harbored conditions favorable for biological processes. The search for ancient life on Mars focuses heavily on rocks and sediments formed during the Noachian epoch when the planet was potentially habitable. NASA's Perseverance rover is currently collecting samples from Jezero Crater, an ancient lakebed that formed during Mars's warmer period. These samples will eventually be returned to Earth for detailed analysis that could reveal biosignatures or other evidence of past life. The European Space Agency's ExoMars mission and future sample return missions will continue this search for evidence of ancient Martian life. Climate modeling of early Mars reveals the complex interplay of factors that determined the planet's habitability. The greenhouse effect from a thick carbon dioxide atmosphere, possibly enhanced by methane and other trace gases, could have maintained temperatures above freezing, despite the Sun's reduced luminosity. Volcanic outgassing from the planet's more active early geology would have continuously replenished atmospheric gases lost to space, at least temporarily maintaining a thick atmosphere conducive to liquid water. The concept of migrating habitable zones has implications for understanding habitability throughout the galaxy and the search for extraterrestrial life. Many exoplanets discovered by space telescopes like Kepler and TESS orbit stars at distances that place them outside their host star's current habitable zone. However, these planets may have experienced habitable conditions in the past, or could become habitable in the future, as their host stars evolve and brighten over time. Future missions to Mars will continue investigating the planet's potentially habitable past and searching for evidence of ancient life. Advanced rovers with improved analytical capabilities will examine increasingly diverse geological formations and drill deeper into the Martian subsurface, where evidence of past life might be better preserved. Human missions to Mars, planned for the coming decades, will enable more extensive geological surveys and sample collection that could finally answer whether life ever existed on our neighboring planet. The story of Mars's journey from potential habitability to its current desert state also provides insights into planetary climate evolution and the factors that determine long-term habitability. Understanding how Mars lost its atmosphere and water has implications for Earth's future climate evolution and helps scientists identify the conditions necessary for maintaining habitable environments over geological timescales. Recent discoveries have revealed that Mars may still possess significant amounts of subsurface water ice and possibly even liquid water in certain locations. Radar observations have detected what appears to be a subsurface lake beneath the South Polar ice cap, while seasonal slope streaks may indicate the temporary presence of briny liquid water under current Martian conditions. These findings suggest that while Mars is no longer in the habitable zone, it may still retain some potential for supporting life in protected subsurface environments. The evolution of Mars from a potentially habitable world to its current state illustrates the dynamic nature of planetary habitability and the complex interplay between stellar evolution, planetary characteristics, and atmospheric processes. As our Sun continues to brighten over the next few billion years, the habitable zone will continue migrating outward, eventually encompassing the orbits of the outer planets while leaving Earth too hot to support liquid water. In the far future, moons like Europa and Enceladus, which currently exist beyond the habitable zone, may experience surface conditions suitable for life as they receive increased solar radiation from our evolving star. The recognition that Mars was once within the Sun's habitable zone has transformed our understanding of the red planet from a perpetually cold, lifeless world to a dynamic planet with a complex climatic history that may have included conditions suitable for life. This revelation continues to drive intensive robotic and future human exploration efforts aimed at uncovering evidence of Mars's potentially life-bearing past and understanding the processes that transform habitable worlds into the diverse planetary environments we observe throughout the cosmos. Fact 21. The universe might contain infinite copies of you. One of the most mind-bending implications of modern cosmology suggests that if the universe is infinite in size, as many theoretical models propose, then somewhere out there, in the vast expanse of space, there exist perfect duplicates of you living slightly different versions of your life. This extraordinary possibility emerges from the mathematical inevitability that infinite space, combined with finite arrangements of matter and energy, must eventually repeat every possible configuration, including the exact quantum arrangement of particles that constitutes your body, brain, and consciousness. The concept begins with understanding the current model of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its first fraction of a second. During this inflationary epoch, quantum fluctuations in the fabric of spacetime were stretched to enormous scales, creating the density variations that eventually became galaxies, stars, and planets. If inflation was eternal, as many models suggest, then this process created not just our observable universe, but an infinite expanse of space with similar physical properties. In an infinite universe, the laws of probability dictate that every possible arrangement of matter and energy will occur an infinite number of times. Since the number of ways that particles can be arranged within any finite volume of space is enormous, but ultimately finite, infinite space guarantees that these arrangements must repeat. This means that somewhere in the cosmos, there exists another volume of space containing exactly the same arrangement of atoms that makes up you, your surroundings, and your entire observable universe. The mathematical framework for understanding these cosmic duplicates involves calculating the probability of specific particle arrangements occurring by chance. Within a sphere the size of our observable universe, there are approximately 10 to the power of 123 protons. The number of possible arrangements of these protons is finite, but extraordinarily large. However, in an infinite universe, even the most improbable arrangements must occur somewhere, including perfect duplicates of every possible configuration within our cosmic neighborhood. The distances to these duplicate versions of yourself would be unimaginably vast. The nearest perfect copy of you would likely exist at a distance so enormous that it dwarfs even the scale of our observable universe. Estimates suggest that your nearest identical twin might be located roughly 10 to the power of 10 to the power of 115 meters away, a number so large that it cannot be written out in conventional notation and has no meaningful physical interpretation within human experience. These cosmic duplicates wouldn't just include exact physical copies, but also beings with slight variations in their life experiences and decisions. In some distant regions of space, versions of you might have made different choices at crucial moments, leading to entirely different life trajectories. There could be versions of you who became artists instead of scientists, who moved to different countries, or who made different personal relationships. The infinite nature of space ensures that every possible variation of your life story plays out somewhere in the cosmos. The philosophical implications of infinite cosmic duplicates challenge our understanding of personal identity and uniqueness. If perfect copies of you exist elsewhere in the universe, what makes you uniquely you? Are these duplicates the same person as you? Or are they entirely separate individuals who happen to share your exact physical and mental configuration? These questions touch on fundamental issues in philosophy of mind and personal identity that have no easy answers. The concept also raises questions about consciousness and subjective experience. If another being has exactly the same brain configuration as you, do they experience the same thoughts and feelings? Would their subjective experience be identical to yours? Or would subtle differences in their environment create divergent streams of consciousness over time? The relationship between physical brain states and conscious experience remains one of the deepest mysteries in science and philosophy. Quantum mechanics adds another layer of complexity to the cosmic duplicate scenario. If consciousness depends on quantum processes in the brain, then perfect duplicates would need to share not just the same classical arrangement of particles, but also identical quantum states. The quantum mechanical nature of reality might prevent truly perfect duplicates from existing, even in an infinite universe, since quantum states are subject to fundamental uncertainties and cannot be perfectly copied according to the no-cloning theorem. The multiverse interpretation of quantum mechanics offers an alternative framework for understanding infinite copies of yourself. In the many worlds interpretation, every quantum measurement creates a branching of reality into multiple parallel universes, each representing different possible outcomes. This creates an infinite number of parallel versions of you experiencing different quantum measurement outcomes, though these exist in separate universes rather than distant locations within the same space. Some cosmological models propose that our universe might be finite but unbounded, like the surface of a sphere in higher dimensions. In such models, traveling far enough in one direction would eventually bring you back to your starting point, similar to circumnavigating the Earth. These finite universe models would not contain infinite duplicates, though they might still contain a large but limited number of similar configurations, depending on the universe's total size. The search for evidence supporting or refuting infinite cosmic duplicates remains beyond current observational capabilities. The distances involved are so vast that we could never hope to detect these duplicates directly, even with the most advanced theoretical technologies. The observable universe represents only a tiny fraction of the total cosmos, if the universe is indeed infinite, leaving the vast majority of reality forever beyond our direct observation. The cosmic duplicate concept has inspired extensive research into the mathematical foundations of infinity and probability in cosmological contexts. Physicists and mathematicians continue to refine models of infinite universes and investigate the conditions under which perfect duplicates would necessarily exist. These studies help clarify the relationship between physical theory and mathematical concepts of infinity that often lead to counterintuitive conclusions. Recent developments in string theory and higher dimensional physics have introduced additional complexity to the cosmic duplicate scenario. Some string theory models propose that our universe is one of many three-dimensional membranes floating in higher dimensional space. In such models, duplicates might exist not just at distant locations within our three-dimensional space, but also on entirely separate membrane universes with their own dimensions and physical laws. The anthropic principle provides another perspective on cosmic duplicates and the conditions necessary for life and consciousness. In an infinite universe containing infinite duplicates, conscious observers will naturally find themselves in regions where conditions are suitable for their existence. This anthropic selection effect might explain why our observable universe appears fine-tuned for life. It's not that the entire universe is fine-tuned, but that conscious observers can only exist in regions where conditions permit their existence. The possibility of infinite cosmic duplicates continues to inspire philosophical and scientific discussions about the nature of reality, consciousness, and personal identity. While we may never directly observe these hypothetical duplicates, their potential existence raises profound questions about what it means to be unique individuals in a potentially infinite cosmos. Whether or not perfect copies of you exist in distant regions of space, the mathematical possibility of such duplicates reveals the strange and wonderful implications of living in a universe that might be far larger and more complex than anything within our direct experience or observation. The concept serves as a reminder that our intuitions about uniqueness, identity, and the nature of existence may need revision in light of modern cosmological understanding. If the universe is truly infinite, then the story of cosmic evolution includes not just one version of every possible outcome, but infinite variations on every theme, creating a cosmos rich with possibilities that stretch far beyond the boundaries of human imagination and into the realm of mathematical inevitability. Fact 22. Falling into a black hole creates different time perspectives. The experience of falling into a black hole reveals one of the most profound and counterintuitive aspects of Einstein's general relativity. the fundamental relativity of time itself. Depending on your perspective, whether you're the unfortunate astronaut falling in or a distant observer watching the event, you would witness completely different versions of the same physical process. This dramatic difference in temporal perspectives illustrates how extreme gravitational fields can distort space-time in ways that challenge our everyday understanding of causality, time, and physical reality. From the perspective of a distant observer, safely positioned far from the black hole, the falling astronaut would appear to slow down dramatically as they approach the event horizon. Time dilation effects become increasingly severe as the astronaut gets closer to the point of no return, causing their clocks to tick slower and slower relative to the observer's reference frame. The astronaut's movements would appear to become sluggish, like a movie playing in slow motion that gradually slows to a near standstill. As the astronaut approaches the event horizon, the gravitational redshift would cause their light to become increasingly dim and redshifted toward longer wavelengths. From the distant observer's perspective, the astronaut would appear to freeze at the event horizon, their image growing progressively redder and dimmer until it fades beyond detection. The distant observer would never actually see the astronaut cross the event horizon or reach the singularity at the black hole's center. They would appear suspended at the boundary for eternity. However, the astronaut's own experience would be dramatically different. From their perspective, time passes normally according to their own clocks and biological processes. They would feel no special effects of time dilation because they're moving through their own reference frame at a normal rate. The astronaut would cross the event horizon in finite proper time, perhaps just a few seconds for a stellar mass black hole, and continue falling toward the central singularity, where the laws of physics as we understand them break down. This divergence in temporal perspectives arises from the fundamental nature of space-time curvature near massive objects. The black hole's immense gravitational field creates such severe warping of space-time that different observers experience time at dramatically different rates. The closer you are to the black hole, the slower time passes relative to distant observers. But you always experience time normally within your own reference frame. The concept of proper time versus coordinate time becomes crucial for understanding these different perspectives. Proper time is the time measured by clocks moving along with an observer. It's the time you personally experience. Coordinate time is the time measured by distant observers using their own clocks. Near black holes, these two measures of time can diverge dramatically, with proper time continuing to flow normally, while coordinate time appears to slow to a crawl. The event horizon represents the boundary where the escape velocity equals the speed of light, but it's not a physical surface or barrier that the falling astronaut would notice crossing. From the astronaut's perspective, crossing the event horizon feels no different from passing through empty space. They experience no sudden change in their local environment, no physical barrier, and no indication that they've passed the point of no return. Only later calculations would reveal that they can no longer send signals to the outside universe. The tidal forces experienced by the falling astronaut add another layer of complexity to their journey. These forces arise because the gravitational field varies with distance from the black hole, creating differential forces across the astronaut's body. The side closer to the black hole experiences stronger gravitational pull than the side farther away, creating a stretching effect colloquially known as spaghettification. For stellar mass black holes, these tidal forces become lethal well before reaching the event horizon. Interestingly, supermassive black holes found at the centers of galaxies create a very different experience. Due to their enormous size, the event horizons of supermassive black holes can be millions of kilometers in radius, creating much more gradual tidal forces. An astronaut falling into a supermassive black hole might cross the event horizon without experiencing immediately fatal tidal effects, potentially surviving for some time within the black hole before reaching regions where tidal forces become extreme. The information paradox adds a quantum mechanical dimension to the black hole falling scenario. According to quantum mechanics, information cannot be destroyed, but general relativity suggests that information falling into a black hole disappears from the observable universe forever. This paradox remains one of the most significant unsolved problems in theoretical physics and affects how we understand what happens to information and potentially consciousness, that falls across the event horizon. Hawking radiation provides another perspective on the black hole falling experience. From the viewpoint of quantum field theory, black holes emit radiation due to quantum fluctuations near the event horizon. Virtual particle pairs near the horizon can become separated, with one particle escaping as Hawking radiation while its partner falls into the black hole. This process causes black holes to slowly evaporate, but the timescales are enormous. A solar mass black hole would take longer than the current age of the universe to evaporate completely. The complementarity principle, proposed by Leonard Susskind and others, suggests that the different perspectives of falling into a black hole are both equally valid descriptions of reality. From outside the black hole, the infalling matter never crosses the horizon, but instead forms a stretched horizon, where information is encoded on the black hole's surface. From inside, the journey continues normally until reaching the singularity. Both descriptions are correct within their respective reference frames, highlighting the fundamental observer dependence of physical reality in extreme gravitational environments. Recent theoretical developments in black hole physics have introduced concepts like firewalls and fuzzball models that challenge traditional descriptions of the black hole interior. Some theories suggest that quantum effects might create a firewall of high-energy particles just inside the event horizon that would immediately incinerate any infalling observer. Other models propose that black holes don't have traditional interiors at all, but instead consist of highly excited string states that occupy the entire black hole volume.